the States he's like much less big. Yeah, great music for sure.
Oh, wait a second. I've been on mute. You've been hearing me, but it hasn't been coming through in the stream. So,
Oh
okay,
well, I guess we're
okay.
still new to the streaming.
Yeah, yeah. We newbie streamers. Well, I am. Okay, so let me begin again. The Tiger Beetle sessions, Monday, 13th December, session two. Hey, Isaac, what's up? How was your weekend?
Hey, alright. Are we do this all again now?
No, it's cool. Have we
Cool.
started again?
All
Any
right.
Anyway, so I was doing some thinking over the weekend about the manifest layout, and yeah, so I think I had an idea that we can solve it pretty simply with a little bit of like fragmentation overhead, but not too bad.
Cool.
Um, yeah, so
Um,
shall I run it by you?
Go for it. Yeah.
Okay, so I thought like we can build it up in stages, and we just try a first pass, and it's not going to be perfect, and then we're going to fix. It's going to have problems, then we'll fix it and keep building on top of that. Um, so so first pass. So we've got like an LSM forest. Um, each replica has the whole forest, and then in a forest there's like 30 trees, LSM trees. Um, each tree has 7 levels. So we've got um, yeah 30 LSMs and 7 levels. And then
Yep.
in the manifest, we're going to do like structive arrays. So we're going to have all the table info fields are going to be, you know, columnized out. So like a
Yeah.
column database. So we'll have 5 fields, roughly like key min, key max, the table creation timestamp. I realize we also want a deleted timestamp, so that we can use the struct of arrays for snapshots and um,
Okay. Yeah. So for all, then we only have like one manifest for all the snapshots. That's
exactly.
definitely better.
In memory, yeah. So it's easier to think about. We've just got created and then optionally like a deleted timestamp, which we can set to a max sentinel. And then,
Yeah.
um, so we've got about 5 fields or, roughly like that order. So 30 trees in the forest, 7 levels per tree, and then per level, we've got the structive arrays, which is 5, 5, 5, 5, 5, going down like that. And then, so the first
Cool.
pass, I thought, what we could do is we could give each level like a contiguous array of memory. That's kind of how we've been thinking, you know. Um, but then it gets tricky because, if you run out of space, you've got to resize it, and then you've got to impact the other trees and steal from them. It's kind of like that idea that we have, moving stuff between. Um, does that, you with me so far?
Yep.
Yeah.
I think I'm with you.
Okay.
Um.
So so so
Cool.
contiguous is quite tricky like that. Then we can go to the other extreme. We can do a linked list, so not an array, but a linked list. So let's just start with that. So that's not going to be great, obviously. So I'll just talk us through, and we can build on top of
All
those
right.
ideas. See
Cool.
see where we're going. I don't know. Have you got an idea where I'm going? Uh,
Not sure yet, but I'm curious.
okay, I'm also not sure. So we'll see. Uh, yeah, I made a few coffees on the weekend, so we'll see if the thinking was impacted positively or negatively. But so the idea is basically we reuse this idea that we had for blocks. So you've got the local storage zone, like 1 terabyte. We divide it up into these 64 kilobyte blocks, and we know exactly how many blocks there are in the storage, and that's how many blocks can possibly be addressed. And that was like quite a helpful insight for us, because then we knew that, okay, well, if you've only got so many blocks, then that sets an upper bound on the number of tables you can have across all your trees, because they all share the storage. So that idea like really paid off on that side of the design that we've already done. So I was wondering, let's do the same thing. So for manifests, this is obviously not going to be a great idea, but let's take these table infos. Let's just think of it as table infos to start. Let's just allocate the maximum possible we could have into a pool and make them all table info nodes that would be part of a linked list. Then
Okay.
each tree can acquire these nodes out of the pool, and we know how many there could possibly be in total because it feeds off of our local storage, total addressable blocks. Um, but so that I think that could technically work, right? It wouldn't be
Yeah, that would
optimal.
be technically fine. It'd just be slow to access because of the memory is not contiguous memory.
Exactly. Yeah.
Um,
So
yeah,
we can't iterate across tables in a level. To if we're doing read lookups, we've got the pyramid of the LSM. Start at the top. Um, we need to go through those tables, drop a level, go through those tables, drop a level, go through. So it's going to be so slow, like iterating across all those linked lists, because it's just
yeah,
pointer chasing, cache misses. Every info is going to be stored in some random location in very slow main memory. So it's 100 nanoseconds per hop. So if we have to iterate across 2 million tables times 100 nanoseconds, um, am I right? Is that like 100 milliseconds?
some 2 million times 100 nanoseconds.
Yeah,
I think that's more than 100 milliseconds.
yeah.
Um,
I think,
Nanomillion is only that thing.
yeah.
Um,
We're warming up. Uh, let's see, it's 100 nanoseconds in milliseconds. Let's see, yeah, it's 200 milliseconds. So
200
for
milliseconds. Okay, yeah,
yeah, for every nanosecond, a nanosecond is a millionth of a millisecond because
yeah.
1,000 nanoseconds are a microsecond and 1,000
Oh,
microseconds are a
yeah.
millisecond. Yeah, cool.
Cool.
So I'm also never sure, so yeah, it's good to have. We need to make this like unit calculator in Python that'll just do this for us.
Yeah, there's some programming language I saw at some point that is like built around this kind of thing. I actually
Yeah,
need to find it again. I think I saw it on Lobsters a while back.
yeah,
Um,
yeah,
yeah,
yeah. Cool. So yeah, so if we do linked lists, it's going to be 200 milliseconds just to iterate across 2 million tables, just because of the
yeah.
memory bandwidth and because memory is so slow. Um, so so that doesn't work. Uh, if if we have a fixed array, okay, let's work that one out. Like let's go back to the other. We've got two extremes now. We've got linked list on the one end. We've got the fixed array on the other
Yeah.
end. So if we have 2 million tables times the size of the table info, let's call it 64 bytes. That is going to be it's going to be 122 megs. We can do 6 gigabytes a second per core with memory bandwidth per core. So it's going to be super fast. Um, yeah, 122 megs, and we can do 6 gigs a second. So six gigs a second is 6 megs a millisecond. So it'll be 20 milliseconds to iterate across 2 million tables. So it's quite a big speed
A
up.
lot better.
Yeah,
Yeah.
yeah,
Power of 10.
yeah. Still seems actually pretty scary. Like 20 milliseconds is quite a long time.
Yeah, that's like for all tables of all LSM trees though.
Mm.
If I'm correct.
Ah, of course, yeah. All tables
And
of all
so if you
LSMs.
divide that by 30 again, then you get it for one LSM tree that's full,
Yeah,
roughly.
yeah,
And so it'd be like less than 1 millisecond.
yeah. Less than 1 millisecond. Cool. And okay. So I guess our linked lists are the same. That's going to be 200 divided by 30 would be 6 milliseconds. Uh, but okay, so we're looking at the fixed array approach is zero point 0.6 of a millisecond. If we do linked lists, it's 6 milliseconds. Those are like our two back of the envelopes.
Isn't that
Uh,
60 milliseconds? Maybe, I don't know.
It was 200 divided by 30 is 6.
Okay.
I think, remember, we had 200 milliseconds for the linked list approach across all tables. So divided by 30, then we get to
Yeah.
6 milliseconds per tree.
Okay.
Is that right?
I think we've got less than 30 trees, but yeah, that's right, I think.
Yeah.
But yeah,
Okay.
30 is for doing this stuff.
Yeah.
Yeah.
Cool. Okay. So then those are the two extremes. And then I thought, hey, like we can do a bit of a hybrid. So what we do is we have our linked list nodes. We can make a node like 1 meg, because now you've got nice contiguous. It's like a slab, and then
Yeah.
as that level fills up, we just allocate a new node. Um, the problem with
Hmm.
making it 1 meg is that then we get fragmentation, because if one node is full, we add another node just to do one table info, and now that's a whole meg that we've allocated. Plus, as stuff gets removed or added.
Right.
And on top of it, remember, we've got 30 LSMs, 30 LSMs times 7 levels times 5 table infos times a meg. We're looking at quite a lot of memory there. Uh, just to give basically we've got a whole lot of arrays, structive arrays. So we've got 30 times 7 times 5. We've got 1,000 arrays that need to borrow from the pool. So even if we all just give them one free node times a meg, that's a gigabyte, 1,000 megs, because we've got 1,000 arrays. So we can't be as big as a meg. But if we make it like 10 cache lines, then we're only looking at 600 kilobytes to give them all a free node.
Okay.
And
That's not too bad. And do you have like a sense of how the iteration speed would be affected by this? Like,
yeah,
how bad are we hurt there?
it's going to be pretty good, because we basically will be doing like 10 cache lines that are all contiguous.
Yeah.
And if we want, we can prefetch maybe. We could, yeah,
If we
we
can
could,
prefetch the next one, then you probably, yeah.
yeah. And
Um,
already like 10 times 64 is like this is all contiguous. So
hmm.
that's not bad. Um, because you see now what we're doing is we're packing, instead of just having one table info in one cache line, we can now pack quite a few elements into a single cache line.
Yeah. Makes me probably do like each node would have like its own structured arrays thing, I guess. Um,
Yeah, so
yeah.
I actually thought we do the structured arrays outside of the linked lists. Um, we well, okay, well that we can see, but maybe I don't understand. Uh,
Hmm. I'm
what
not
what?
sure what you mean by outside then.
Yeah,
Like the arrays would only be within one block of memory, right? Or
yeah.
do you like
So
use a different linked list name for each array? I'm not sure how you're picturing there.
yeah, so I
That'd
was
be better,
thinking
in fact.
I was
But yeah.
thinking let's just have key min. That's the only thing. We don't even worry about all the other table info fields. Um, let's just say we're for one tree, we're only looking at level 3, and for level 3, we're only thinking about the key min array. So key min array will be this special like contiguous linked list structure. I don't know how we wrap it up outside that. We can make it nice and clean. Uh, but basically, the linked list for key min at level 3, that'll just have access to a pool where it can get a multiple of cache lines that are byte. The type is bytes, so that it works across all trees regardless. We don't have to make it generic,
Right, yeah.
like we've done before. Um, so we just get a multiple of cache lines allocated to the node, and we'll be pretty good then, with fragmentation as we go. Um, and then I was actually looking after I was, like trying to create this hybrid, and it turns out this is actually like a data structure. I've never heard of
A
it
pool
before.
allocator or what?
This linked list idea where the nodes are more than one
Yeah.
element.
I've seen people do that before. Yeah.
Yeah. Yeah. Do you
Um,
know? I didn't know the name for it. Do you know like what it's called?
um, I don't know.
Anybody?
There's like some C++ library that like replaces the standard library linked list with something more like this, which is
Yeah.
then the PLF list thing.
Yeah.
But that's not really a good name for the data structure. You could call it like a segmented list maybe or something like that. I'm not sure.
Yeah.
Um,
Cool. Yeah. Selective duplicates just joined. Says greetings. Great to see another stream happening. Good stuff. Awesome.
cool.
Yeah.
I
So
got the chat
maybe.
in my end.
Uh,
I've managed to
okay.
join over IRC.
Hey. Awesome. Awesome. So I don't know. Shall we give people like a few seconds if anybody knows what the structure is called?
Cool. Sorry?
Yeah. I thought let's give people like a few seconds, see if anybody knows. Okay, time up. So
All
yeah,
right.
I never, yeah, basically I didn't know the structure before, but it's called the unrolled linked list.
Unrolled. Okay. Sure.
Yeah. And the way it works, the fragmentation basically works out to be like 75, it's 75% efficient. So we'll have like a 25% of that is like unused nodes overall,
Okay.
you know? Um,
It also makes it so we don't need to do the mem copies though when we reallocate stuff. So that's
exactly.
about very nice.
Yeah.
Um,
Yeah, because if we have like say we've got 1,000 tables or 10,000 tables all contiguous, now we need to grow
yeah,
that slab. That's a big mem copy, which is like a big.
that's
Whereas
a
the
latency spike.
yeah,
Yeah,
now we only do the mem
but
copies
it's
within
definitely
these
nicer
little
from that perspective.
yeah,
And you have basically your pool allocator that has a bunch of these buffers, and you just assign them to trees as necessary.
yeah,
As
exactly.
follows the same pattern as the block reset. I think it's a good way to approach this.
Yeah, yeah,
Um, yeah.
cool, cool. So we do pay like a bit of overhead, just like 25% of
Yeah.
so but I think that's okay. I don't know if you feel that's acceptable.
Yeah, I think it is acceptable. I think we just need to tune like I think we can use fairly large nodes. I think we don't need to keep them super small.
Yeah.
Even if they're megabyte in size, I think that's probably fine. Um, because our trees will mostly grow at similar rates.
Yeah,
Like I think making them quite large is okay. That's kind
yeah,
of my yeah.
yeah. So we make them bigger than 10 cache lines. We make them like a kernel page, like 4 kilobytes. Uh,
Something like we could do that, yeah, something
yeah,
like that.
yeah,
I think there's no reason to make them smaller than that for our use case because yeah, we'll have like maybe waste a tiny bit of memory, but I think that like makes the overhead a lot lower to
yeah,
make the nodes just larger because then you have
yeah,
one cache miss every 4 kilobytes instead of every 10 cache lines.
yeah,
You can also then prefetch maybe we can benchmark if prefetching really helps there, but yeah,
yeah,
we've got the built-in influence now upstream, so yeah.
yeah, yeah. Cool. And yeah, so if we do like 4 kilobyte pages, we've got 30 times, like on the order of 30 times 7 levels times 5 fields. So it's basically, call it 1,000 arrays. And each of them
Yeah.
need to have at least one free, well, they don't even have to have one. They can take it if they need it, if they even get
Yeah.
to the bottom level. But but say they all have one free one because of fragmentation. So then we're looking at 4 megs, which is not a problem.
I think it's fine. Yeah. Cool.
Yeah, yeah. And then maybe we should ask DJ if this is something he'd be excited to do, like how he's done the block reset. He could do the unrolled linked
Yeah.
list.
I mean, it's pretty fast to do, I think. But yeah, it's basically a pool allocator is what I'd call this. Like the structure that gives you these things, which is the same thing our message pool is for the message bus.
Exactly, yeah.
Um,
Yeah.
it's
So
just
I
like an
think,
allocator that can only allocate fixed size things, and
yeah,
you just basically have a sense of one allocation time there because you just store a linked list of them in a free list,
yeah,
um,
yeah. So I
which is
was
nice.
thinking like DJ could do the unrolled linked list if he's keen, and we could give
Sure. Yeah.
him we could give him an allocator. So we create like an unrolled linked list which takes an allocator. It's unmanaged, so all the methods take an allocator, and we will provide that allocator. Then we're keeping it more general, and this is maybe something the standard lib could use, or we just don't.
Okay.
What do you?
I think the linked list implementation shouldn't have any way to allocate memory. I think it should just take a node, like the standard lib linked lists do. Like the user just provides the nodes, and the linked list implementation really just provides the node type and a way to iterate. That's all it needs to do.
Okay,
It doesn't need to worry about where the memory comes from for the nodes.
okay,
That's how the standard lib linked lists currently work, which I think is good.
yeah,
So they have other issues because they're not intrusive and kind of weird sometimes. But yeah,
okay,
um,
yeah. So yeah, do you actually want to code this up then? Like, shall we do the unrolled linked list?
we
We I
could,
th
yeah. Um,
I thought we could also see how we use it as a struct of arrays, and we could do kind of like what we've done so far, where we just plug in APIs that we haven't implemented yet, and we can
True.
carry on with the manifest, and we can also see how we use the unrolled linked list. Because what I was thinking so far is we don't want it to do anything sorting. We just want it basically say like at this index, insert an element, or we call it yeah, maybe an element, then we're not overloading value. So we use value as a name in the rest of our assembly land.
Yeah.
So basically at a given index, insert a value, or at a given index, remove a value. Um, at a given index, look up a value, and then the keys unrolled linked list will need an iterator so that we can scan across it to
Hmm.
to for sort
Yeah.
order.
So insert and remove are gonna be expensive though. If you're inserting to the middle of the list,
Uh,
right?
yeah,
Is
because
that
you've got to.
problematic?
Well, that's pretty exciting actually. Like because like a normal linked list, you've got to. It's expensive because you've got to iterate. You've got to do on like potentially to get to the end of the list, and then finally you remove something. Um,
Right.
these unrolled linked lists, you get it's a mix between linked list and array
Well,
behaviors. So
it's like O(n) divided by, it's still O(n) complexity, but it's O(n) divided by your block size, I
exactly,
guess.
you get to actually skip. So if you know that you're inserting at index 1,000,000, you basically go through a block and you know how many are in the block. So you already can jump to the next block and on and on.
Yeah, yeah.
Yeah. So it's
Um, but say you remove the first element in the list, do you now have to shift all the memory of all the other elements in the list, just like a contiguous array?
no, no, you don't. You just shift the elements in that node that you've modified.
Okay, and so then you like add some free space to that node essentially.
Exactly. And then when you do that, if you decrease the size of the node, you can check in the two neighboring nodes if you can get rid of them. It actually gets quite, you can make it quite detailed, like how and we can be as aggressive or conservative as we, or lazy as we want. So
Hmm.
so typically like what they do is if you want to insert and the node is full, then you allocate a free node and you copy half of the elements in this full node into that one, and then you put in the insert. Um,
Okay.
that's what you do. Um, but what we could do is it depends how tricky we want to get. If this node is full, we can see, oh well, we're inserting at the very end of the node. So then instead of doing that, we could check the next node, does that have space, and put it at the beginning. That's like a little optimization. Uh,
Okay. Yeah. And
or,
so, yeah, so that makes it then much more of a trade-off how big we make our block size then, because then the larger block size makes it more expensive to insert and do like random access or do insert and removes in the middle of the list
yeah, yeah,
potentially.
yeah,
So that's the trade-off then with the block size.
yeah.
Do we really need to do that though? Like, what's our access pattern for manifests? Do we really need to insert and remove from the start of the list or the middle?
Well, that's the thing. Inserting at the start or the middle, there's no difference in cost. The you
Yeah,
only
well, it's
you're
still
only
more
doing
expensive
mem
than paying to the end.
No, it's like the same. So if you wanna, if you wanna, it's basically like a linked list. You've got very good insert performance for the actual insert, um, because you basically putting stuff into a bucket. If the bucket has got free nodes, you have to do a little bit of a mem copy. So if your bucket is like 4,000 bytes, you just maybe shift a few of the items. That's it, and put it in. But
Right.
that
Yeah.
it's limited to the size of the bucket.
Yeah. I'm cool with that. It's still depending on the size of the bucket, then more expensive. If we
Yeah,
want to make iteration faster, then inserts get more expensive. I'm just
exactly.
wondering if we ever need to actually insert. Do we actually need to insert though? Like what's the
Yeah,
usage pattern there?
yeah. So we only need to insert when we're creating new tables through a compaction. But for
Okay.
every time we insert, we're going to be doing 100 times more lookups, like reading these structures. So they're
Yeah.
very read heavy and they write light. So we want to optimize for bigger blocks. But I mean, it's still like yeah, like so I think for a compaction, if we have to copy a kilobyte or so, it's not a problem to insert a table. What do you think?
Hmm. And so the lookups though, they're gonna be we're gonna be doing like binary searches on this, right? Find keys essentially. Or what is the lookups gonna look like?
Yeah,
'Cause maybe we
that
want like a different data structure, like some kind of tree. I'm not sure.
yeah, I think we do because our iteration is not great. Like we're at like
Yeah.
a millisecond.
What's worse than the iteration is the point lookups in the array. You can't really just index into a node without then iterating over all the nodes up until that point. So if you want to look up the middle node, you've got to start at the beginning and iterate over all the nodes to get to the middle. That's
Yeah,
ON random lookups, which is sucks for binary search.
yeah,
Um,
yeah, yeah, yeah. Well, it wouldn't be as bad as ON because it's divided by that ON would be linked list. This
it's
would be
still
some
ON
way
complexity though. I
it's
agree that it's faster than it would be if we had a normal linked list, but it's still ON. Um,
it's ON divided by the size of the
yeah,
yeah
yeah, it's faster than an ON would normally. Than it's faster than it would normally be, but it's still ON complexity. That doesn't change. Um, um, and
okay,
the complexity
okay,
grows at the same rate. It's then offset by like a constant factor because we've like made blocks, but still it's not constant time lookups. It's now based on the size of your list.
yeah, yeah.
Um,
Yeah, but I mean, if we made the blocks huge, then we would have an array. Well, the idea is that this structure gives you something you can tune. So if your block is 1 gigabyte, you've now got an array. So you've got O1.
yeah,
You can do lookups in O1. If your block is 1 gig, your node is 1 gig, you've got an O1 lookup. If your block is only can contain one element, then you've got ON complexity lookup. So you can tune it.
yeah.
Uh,
I'm with you there.
yeah,
I understand that. Yeah. I'm just thinking if we could then just actually use a tree of some sort that would make it look much faster still. Um,
yeah,
and you can do a tree with the same kind of like pattern where you have like in each node of the tree you've got a whole array of data,
yeah,
but then you structure them differently in the linked list, and so you put like your middle keys in the middle of the tree
yeah,
and kind of do things like that.
yeah. We're gonna have to do that. I wasn't even thinking that far as like the binary search. I was just trying to solve the how do we do allocation across all the trees so that we don't have to do
Okay.
these big
Yeah.
mem copies for like if we treat it
Yeah.
contiguously.
I think you're right that having a pool allocator is the way to go here,
Yeah,
and be able to use that pool allocator for our data structures. Because the pool allocator is really great because it has O1 allocation time. It's very simple, and then it just like lets the trees decide how to divide the stuff between the trees at runtime,
yeah,
very simply. And
yeah,
so that's definitely a good approach there, I think. And I think that we need some sort of tree structure though for our actual lookups or something that's faster to than query, but
yeah,
also in sort order. And so I
yeah,
think just a sorted binary tree or like a red black tree or something like that is going to be what we go for.
yeah,
Um,
yeah.
I think there are ways to do those things with good iteration time too, because you do the kind of the same trick as this linked list where you have then multiple items per allocated node. Um,
Yeah.
Maybe that's a
Ex-
B tree then. I'm forgetting. There's a whole bunch of different trees. We need to go
Yeah.
back to theoretical computer science, look up all the tree kinds.
Yeah,
Um,
exactly. Yeah. Yeah.
yeah,
No, I'm with you on the tree because otherwise, like you said, the lookup performance will suck.
yeah. As a binary search on a linked list just sucks. No matter how good your linked list is, it's still on random lookup
Yeah.
complexity.
Yeah. And binary search on an array, that's okay.
And then you've got O1 lookup, but yeah, that's fine, I guess. A tree will give you it'll be the same as like a tree lookup. It's the tree is also O log n. Um, Binary search on a linked list is O n log n is the problem instead
Yeah.
of just O log n.
Yeah. I was reading about these unrolled linked lists, and they were saying, I don't know if you want to look it up on your side. They were
Sure.
saying it's sort of
Um,
similar to a tree because of how you can skip over nodes. Um,
they're optimized for iteration though, not for like a search.
yeah.
Did you find a Wikipedia page or what were you on?
There's Wikipedia, and there's a few. There was one very good one, like a coding one. I don't know exactly which one it is. Um,
Yeah, so I think a B tree is what we want in memory perhaps.
yeah,
Um, that's kind of the tree with like blocks at each node.
yeah. I'm keen on a B tree. I think array layout for comparison-based search, they were actually
Yeah.
saying a B tree, and I think in there they made some comments that a red black tree was not so great, the edge case performance and stuff. So
Yeah. I think
they
a
were
red block tree
thinking,
usually they just do like one element per node, but with a B tree that's it's the kind of the whole thing is that you have multiple elements per node.
yeah,
Um,
yeah, okay. So you're happy with this? Like we do a B tree using pool allocator.
Using a pool allocator to allocate the nodes, I think that's actually perfect.
Yeah.
Um, yeah,
Okay, cool.
that seems good for what we were doing here. And
Yeah,
so I think you want like then just go ahead with the manifest implementation, like assuming we'll have this data structure
yeah.
and see how that works out.
And then
See if we hit any showstoppers.
yeah, and then are you keen to implement that structure as well? Then we go and do it like
B tree?
once we know the
Yeah, we can
API.
do that.
Yeah.
We can either do that or let DJ do that, but just like see what makes sense. But yeah, I'm happy to implement that. I've done that before, like once long
Yeah.
ago in some CS course in C++.
Yeah. Yeah. My tree knowledge is it's pretty funny that we're building. I mean, I'm happy with LSM trees. That's cool. But
Yeah.
otherwise my tree knowledge, I'm not much of a gardener, like that's yeah. So I wouldn't mind to
Well,
implement it just to learn, like understand it a bit better.
sure. Yeah, we can do it together then.
Yeah.
Shall I share my screen and get going
Yeah.
then?
Yeah. Let's go for it.
Cool. Um, just looking at what we had done last time. So we've got here some uncommitted stuff we should probably commit before we move on, actually. The super block modifications mostly.
Yeah.
Um,
Cool.
so yeah, let's do those real quick, and then we can get back into the manifest stuff because we got those two things here. Um, Store stage dot. All right, direction no, super block stuff yes. Um, Recovery also yes. Now we've just got super block stuff staged. We can commit this, I guess. Um, Is that what we did? This is now, well, I guess we changed the manifest layout in the super block. This is more like move manifest to the trailer. Move manifest. How's that?
Yeah, we can maybe, what do you think? We can say this reduces the size of the super block by significantly down to a single disk sector and decreases the latency of checkpointing the super block. Yeah.
And the tree isn't full. Full. Um, also, how's
Maybe
that?
maybe we can just say reducing um, the latency of checkpointing the super block, so people know which latency it is. Reducing the latency of checkpointing the super block significantly.
Checkpointing the what?
Checkpointing the super block.
Cool.
Yeah, cool.
All right. There's that done. Now we've got now just like the LSM tree stuff we started working on, or the manifest stuff we started on, so we can just keep on going with that now.
Cool. I'm going to pop your screen big as well.
Hmm?
I've just popped your coding editor full now. We were giving us
Oh, cool.
three equal blocks. Now we're full on into Cocoon.
Now we're full on coding. Nice.
Yeah. Hey, by the way, Isaac, I was practicing my multiple selection over the weekend. I got it going nicely in Sublime. So
Nice.
yeah,
Like with the selecting forward and backwards and getting rid of them and whatnot.
yeah, and
Yeah, I'm sure there's keybind Sublime
s-
too.
skipping
Yeah.
over all of that, like all the ones that we need.
I find it a lot easier to do in a modal editor though, because in Sublime you've got to use like a whole bunch of control and alt keys to do that stuff, right?
Yeah,
Well here in
yeah,
command
yeah,
mode, then you just use like normal single keys without any modifiers
yeah,
to do a lot of the actions.
yeah.
Um,
It's actually like just three
that's the main
keys,
difference.
three modifiers, but they're all next to each other on my keyboard. So it's like zip, and then it's okay.
Okay.
Uh, I I must still get my head wrapped around modal editing, the simplicity of the
Yeah.
keyboard shortcuts. Yeah,
It does definitely took me a bit to get used to Vim when I first started doing it, but then switching from Vim to Cocoon was pretty easy.
yeah,
Um,
yeah,
yeah. But I don't think I could go back at this point. It's too like in my fingers at this point now.
yeah,
Um,
exactly.
yeah. All right. So where were we at here? We have our table index function. Mm. Yes, maybe this isn't really an index anymore, but like a pointer or temporary pointer to um into our tree.
Yeah, a point is probably more efficient to
Yeah.
do it that way.
So we need to kind of think about what kind of iterator interface our B tree would expose.
Yeah,
Maybe this is actually an iterator that like then would return like the current value and then the next one, the next one, the next one. We just use it once here or something like that. I'm not sure about that, but yeah, we definitely got some things to solve here still.
Yeah.
Um, you only need the tree for the keys actually, so we might want to store the rest of the stuff separately from the tree. So we only
Yeah.
ever look up by key. There's a lot of different things to solve here still.
Yeah.
Um,
What we'll do, like, if like, shall we sketch it all out and like step through it for all the scenarios and see how it works? Like talk it through.
sure.
So if we've got a, like, say we've got a point lookup coming in, now we're looking, we've got the in-memory tables, but we're not looking at that yet. Now we're looking at the, like the man, well, actually, yeah, we're looking at just the manifest for the on-disk tables now. So we'll start at a level. We want to know, find tables that overlap the key, find tables that could contain the key. So we're looking at key min,
Yep.
and then if so say the key is 123, and then in the level we see the table has key min of 0, but it has a key max of 10,
Yep.
then it couldn't contain the key. So we keep going. But we've got to look at key min and key max.
Yeah. And so yeah, so I think we want to we store things in our tree. Like a tree should be sorted by key min. And we also probably want to store key max in the tree perhaps to make that lookup then also fast.
y-
Um,
yeah, because we don't want to like bias key min. We want to, it must be the same for key min or key max so that no matter which direction we're
yeah.
going, it's the same
So
thing.
I think we should. I think the simplest thing to do here would be just to store the table infos, not destructive arrays, at least not to start with. Just store the table infos directly in the B tree.
Okay.
Um, that's the simplest mental model for us right now, because then you can just easily then access key max as well.
Yeah.
And then I think there may be a way to make that more optimal than by storing some stuff like out of with another indirection, just to make the B trees have less stuff in memory, make like the searching faster.
Yeah.
You could then like have a contiguous array as well, and then store like an index into that to get like the rest of the table data, like the address and checksum and whatnot.
Yeah.
There's some tricks you can do there, but I think that makes our mental model too complex right now.
Yeah.
Um, we should just think of it as a B tree that will give you a pointer to a table info, essentially. Um,
Okay. I was thinking of that to start on the weekend, and then I realized I'm happy if we keep thinking like that for a simple mental model. Um, there's
yeah.
one there's one area where or two areas where the structive arrays. Are you thinking eventually we will do structive arrays?
Well,
Just to
I'm not sure
understand.
what that would look like with a tree. Um, yeah.
Yeah. So I think the yeah, maybe we must just do a tree of table infos. But
I
one
think that's
adva
the start. That's the
what
conceptually the data structure we want, but then we
yeah,
just need to figure out how to make it optimal for our use case.
yeah. Because obviously if we don't have to store we only searching by sorted key min or key max. The other stuff we just need to do an index lookup as if it's a fixed array. We don't need that stuff in a tree because then basically the less stuff we put in our B tree, the quicker it is to search because
Right. Yeah.
um,
And so my idea was to have we could do the segmented list for that stuff then perhaps. Um, I'm not
unrolled linked
sure.
list.
You
Yeah,
still then have like your kind of index lookup when you do eventually need to do it, but you're not doing that lookup repeatedly while you're searching. That's going to
exactly.
be fine.
Yeah.
Um, but we would then store like hmm. So linked list of stable indexes. It doesn't have stable indexes or pointers, does it?
It does. Well, we could make it. I mean, like the pointers would be stable until you do another insert. Uh, but indexes are fine. Like that's just you'll give it an index, and that's where it will put it in.
Yeah, I'm just trying to figure out how you would get from and the table info or the key and key maxed in the B tree
Yeah,
to the data in the use array or linked list or whatever it ends up being. I
yeah,
don't see a fast way to do that.
yeah.
So if you store
Cool.
indexes in the B tree, you've got to keep them in sync with the indexes on the linked list,
Yeah,
which means like doing all the indexes when you insert something, which is not feasible.
yeah,
Or if you store pointers, they're broken because your linked list actually moves data around as it inserts stuff.
yeah,
Be able to keep it fast.
yeah.
Um,
I'm with you. Just another motivator, like it is that the different trees have got different keys. They're generic over the keys. So some of them have like a key size of 8 bytes, some have 16 bytes, some have 32. And because of that, the table info is either going to be like 32 bytes plus 8 plus 8 is 48 bytes. Basically, our range of table info sizes is 48 bytes, 64, 96. And
okay, based on the key size, yeah.
And then it gets tricky because we could try and multiply all of those by a factor so that we end up on a power of 2. So what we basically want to avoid is for our pool allocator that gives us nodes, we don't want to have any padding in the nodes. Um,
Right, yeah.
so if we're storing table
Hmm.
infos in the nodes, we're going to end up with padding because it's pretty tricky to get a node size that's a perfect multiple of 48, 64, 96.
You know, I think you can get indexes from a B tree. Like when you insert stuff, you can like do some bookkeeping to keep track of which index every element has in the tree. It's a
Yeah,
sorted tree.
exactly.
And then we can use that to index into the segmented or the unrolled
Unrolled.
linked list.
Yeah, yeah,
Let me see what Wikipedia has to say there. It's
yeah.
probably not big enough.
Because
That's
if
probably big enough.
again, like the nice thing with structive arrays is then we don't have padding issues anymore because all our fields are 16 bytes, 8 bytes, 32 bytes. So if our block,
Yeah,
then the padding disappears again. Um, what do you also like that?
I think I definitely like having that separate. Yeah,
Yeah,
that definitely makes sense.
yeah,
Then we have just the trees generic over the key type, and then that gets faster for the smaller keys, which is great.
yeah,
Um, and then the other stuff is like all basically the same for all LSMs and doesn't even
yeah,
need to be generic,
yeah,
which is also
exactly.
cool.
Yeah,
Um, I'm not finding anything about it here in Wikipedia, but I think it says in the implementation part, sorted order, hierarchical index, partially. But I think you can just kind of like add a little bit more data to the nodes to store like which or how many elements they have, and then elements of the children essentially up to the root. Then the root node kind of stores how many elements the whole list has, as well as
yeah,
each of its children or something like that.
yeah,
Not sure. I'm sure we can figure it out though. Some way to do a little bit of extra bookkeeping to keep indexes.
yeah.
Um,
They
and then we
in
can return an index here.
yeah
Um,
in the Kong and Pat Morin paper, they talked about B-trees doing bookkeeping to return the index when you
oh, easy then. Then they
yeah
probably got it in like array layouts. Let's go
yeah.
look at that real quick. Okay.
It's not as efficient as Eytzinger Layout because we
Yeah.
can yeah to B-tree you've got to do the bookkeeping while you're doing the search loop.
Okay.
Eytzinger they
Is
have
this
that
this
cool
then?
bit
Branch
hack.
research. Mm, Well, let's first understand their data layout. It's a B tree inside an array. I think this is a B tree backed by a single array. I think. Um, yeah. Okay. Copy data. Yeah. So for data I is greater than or equal to n. Return E0. They just kind of go through and call copy data recursively on the child. This B. Yeah, these it's not very easy to read, is it? We don't know what these indexes really mean. I
Yeah.
guess you might know if you're already like very familiar with B trees, but I'm not picking this up just from reading it. Anyhow, they do
Yeah.
something there. We can come back to it when we implement the B tree.
Yeah. Yeah.
Um,
I think you've already seen this before me, but like the we put the key min and key max into B trees, depending on
yeah,
which direction we use one of the B trees, or we put them both into one. But
I'm
once
gonna go
you've
on the
done,
same B tree.
okay,
Um,
but once you've done that, that's the only thing where the key size is variable.
yep.
All the other table info fields are always the same across trees.
Hmm.
So, and it makes sense then for those, like for times, for creation, created timestamp, deleted timestamp, it makes sense for that all to be contiguous, not to be split up into each struct of arrays, because otherwise we'll look up the key. We want to go check the creation timestamp and the deleted timestamp. We don't want to do separate cache misses each time.
Yeah, as
So we
long as
want,
there's no, I think there's no padding there either, is there? I
no,
think
there
we have,
isn't.
so, well, if we have another timestamp, then there's a bit of padding with the checksum. We've got the two keys, which would be in like the B tree. Then we have two
Yeah,
timestamps, an address, and a checksum. Then there's like 64 or 8 bytes of padding essentially.
yeah.
Um,
We could, um, it might be that for compaction, we'll want to keep some stats so that we can pick tables like based on how many things they
hmm.
contain. So we might
So
want
we can
to
just
add a
say the padding is
usage.
fine, and we might use it for something in the future.
Yeah, like how just so we can know like this table has roughly like 1,000 entries.
Sure.
So
Yeah.
I don't, but it does make sense that once you have located the table by key, everything else you want to be all contiguous. You don't want to do separate struct array lookups for those. So,
Yeah. That makes sense.
yeah,
I'm trying to think if there's a better way to do this. Now it seems like we should just have a pool of table infos in a single contiguous array shared by all the trees, or something like that. Or not the table infos, but like this part of the table info, like the checksum address and two timestamps.
yeah,
That could be potentially shared by all the trees in like one allocation.
yep,
Um,
yeah. And the order of them doesn't matter. They don't have to be in any order.
yeah,
We
it
just
can
need
just
an
be
index to
like
them.
a pool
Yeah.
somehow, like with another preset thing. I'm not sure.
The only thing too is that we need to remove them from that array without copying everything. Um,
Right. And so you could use some kind of like free bit set like we do for the disk sector or disk blocks. Um,
okay, cool.
I'm not sure that's actually the best way to do it though.
Yeah, no, that's pretty cool. I think that's better because that'll give you array like indexing, O1, just better than the
Yep,
unrolled linked list.
exactly. And if
Yeah,
you keep the stable indexes, then you can just store in your B tree then you store
yeah,
two keys and an index into this array.
yeah,
Um, yeah.
cool.
So it would be nicer if in the tree the index didn't have to be stored in memory. It was just like kind of implicit from the place in the tree. Um,
Yeah,
I'm not sure how that works out, but I think there's a solution there, and we should focus on like the higher level implementation somehow now. Like we should just use the mental model of just having a B tree of table infos
yeah,
essentially.
yeah,
Um, Work on then the actual functions we need here to make sure we've got all the cases covered that we actually have. Do you agree with that?
yeah, yeah, that's cool.
All right. So I guess we're then already running into implementation stuff where we this table index function that now might not return an index. That might just like return a table info pointer. I'm not sure.
Yeah,
Um, we can just like call it handle for now, but it like represents a position within our data structure because we want to be able to start iterating from there. Um, Maybe that's just maybe this is just the wrong API now, where we
Yeah,
just want to get a table info.
maybe
Um,
maybe we should scratch a lot of this and um, just just do like just talk it all through in pseudocode, like for point lookups, for range queries, and range queries do compaction as well. Uh,
yeah, well, I think this table function's still got the right signature.
yeah,
Um,
yeah,
level. No, we haven't talked about levels yet.
yeah,
Do we need a separate B tree for each level? Is that what we
exactly.
do?
Yeah, definitely.
Cool.
Yeah, yeah,
So we just have 7 B trees, and the level gives us an index into our array of B trees, I guess.
yeah,
And then we're good. Um, cool. And then table index, this is just going to return. It's not a thing anymore, I don't think. I think we just go to like manifest.btree. Um, we do like const info gives manifest dot levels level,
yeah,
and then dot get and pass in the key, and that's it, I think, and snapshot as well.
yeah. I've got a little curveball, but maybe it's also going to help us. Like
Okay.
maybe maybe what we need to do is think of compaction first, like solve the compaction use case, because once we've solved that, the others are just refinements of that. That is like the high resolution thing, and the others can be derived from it, you know? So what I'm thinking is that when we're doing compaction, we'll pick a table and then we want to go to our manifest into the level to level B. So we'll pick a table from level A, then we'll go to our manifest for level B. And what we really want to do is find all the tables that overlap table A's key range.
Yeah.
So maybe what we must do is rather have an iterator for a level that will find you the first table matching the key range, because that will still work if you're doing a point lookup.
Well, I'm just thinking that's a different API on the B tree. I think the B tree has a get function and a function that do iterators, and this is already done now, is what my thought was. Now we can move on to that part. Um,
Yeah, okay.
I think this is now like, I think our B tree will need have a get function, and that's pretty simple to implement. Just gets a table info for point lookups. Um,
But what I mean is that a point lookup, okay, because you see, then our B tree will have to store things not only sorted by key, but also by timestamp, so that there's precedence like for level zero, because level zero can have overlapping tables. That's the other problem.
hmm.
I just thought
Okay. So
before
you're
we
planning
get
us to
into
implement
the,
level 0 kind of differently, where we then like query we get all the tables and then search them outside the B tree. That makes
yeah,
sense.
I was thinking we should just talk everything through before we think of B tree or think of implementation. Just think of the
Okay.
API we need. Because when we query level zero, we want to get all tables that overlap the key. And that's the same that we need for compaction, but at any level, get all
Yeah.
tables that overlap this key.
Okay.
So, but in both cases, it's an iterator that we'll use.
And yeah, and it
Even,
may just be one table, of course, but yeah.
yeah, I don't know. And we can always like do it, like do the use case for compaction, and then later on we can see, can we optimize it for point lookups? But if
Yeah,
so,
sure.
and when we do it for compaction, we also want to, compaction and range queries are like the same. So we want to make the direction first class.
Yeah, so it's this API, right?
Yeah,
Get tables.
exactly. Yeah. Maybe that's all we need now.
Our iterator returns this thing. We just need to figure out how this works, I guess. Um,
Yeah. And we just need to, so get tables will also take precedence into account. If the if the tables overlap in the level, then it will return them by newest table first.
hmm. Okay. Can we just can't we make our trees sorted by by precedence then? Like we're gonna have to press like a compare function, like
Yeah,
you compare keys to the
yeah.
B tree. That could then, if the keys are equal, fall back to the timestamp pretty easily. That's what we do in KY merge, for example.
That's how we do
Um,
it. Yeah, yeah. So that's this. That's cool
and
then.
so then I don't think we need this. We just take the first key. Or we don't need this to like then do the tie breaking for level 0. I can just take the first thing that appears in the B tree that's already been then sorted by timestamp. Well, maybe snapshots make them more complex, but yeah.
Yeah.
Um,
But what I mean is maybe let's ignore the point lookup case first and solve range
yeah, I'm,
queries.
I'm with you there.
Yeah, yeah.
Yeah,
Cool.
but yeah, I'm thinking we don't need to like do like order stuff by timestamp in this function. It should already be ordered in the tree.
Yeah,
Um,
exactly. And we do it like we did for KW merge, where the
hmm
exactly as you said. That's yeah. I was just adding it in just so we remember it, so that it doesn't become a
for
showstopper
sure,
later.
yeah.
Yeah.
So the snapshots, do these get implemented in the tree or in the iterator? I think these go in the iterator now. Um,
Yeah.
and
Yeah.
so the iterator will get returned to table info, and then for the key we queried or the minimum key we queried with, um, then it's the first thing we do is like look at the snapshot to see um, is this table more recent than the snapshot timestamp? Is the table timestamp greater than the snapshot timestamp? If so,
Yeah.
just skip it. You move on to the next one and query the tree again.
Yeah. And
Um,
if the table's deleted timestamp is less than or equal to the snapshot, then we also skip it.
yeah, so I think the B tree is going to have its own iterator type essentially that just gives us the table infos. And this iterator should be a wrapper around that type, so we don't have to repeat the lookups in the B tree. Um, so does that make sense? I
Yeah.
think
So
we
are you,
should create like a B tree iterator that then we we just give a start key and then it gives us every table in order after that key without doing a repeated lookup.
yeah.
Um,
Yeah. Exactly. Yeah. Definitely. We could
and then
like
here we wrap the iterator and like take snapshots into account and also the end keys or something like
yeah.
that. I'm not sure.
What do you think if the B tree actually does everything and the B tree knows about snapshots and precedents and deleted created timestamps?
I think that's going to be trickier for us to implement. I think having we maybe should do that in at the like in the future for as an optimization if that is an optimization.
Hmm.
But I think keeping it separate for now will be better. I
Yeah.
think the B tree should only know about the min key as the B tree's key, and then the value, which is the rest of the data. It shouldn't even know about max keys. Um,
But then we will need a separate B tree for max keys when our direction
no, we
changes.
won't. We'll query by min key and then like iterate backwards or something like that.
Okay.
Um, I think.
Yeah. Okay. That makes sense.
Because
Because
when
whether yeah.
you query by max key when you want to, or when you want to like iterate in reverse, right? That's when you would
Yeah.
use that.
Yeah.
And so we like query by min key, but we just use like we pass in the min key or we pass like the max key we want to start at as the min key in the B tree query. Um, and we find like the first table. Um, I guess past that we find like the first table. Well, I think we find the first table then that has that key in its range, or has for which that key is greater than the min key of the table. That's what it would be. And then that's in the table we start iterating at, but we then iterate backwards. I think that all works out great.
But
Um,
we then need to look at the max key as well, because sometimes the key can be greater than the min key, but also greater than the max key.
okay, right.
Yeah. And I think what we should do is put the key min and key max together in the B tree because
Yeah,
we're gonna always look at them both. But we can like you say we can sort the B tree just based on the key min. It'll work for both
key min, but then also
directionals.
I have the queries that B tree should look like key max as well, probably. I think you're right there.
Yeah.
Um,
And we want to keep those contiguous in the big B tree so that we don't have to do another cache miss to
yeah, maybe it does make sense to do all the stuff in the B tree. I'm not sure. My sense is that it'd be nice to have it a little bit separate, just to keep the B tree simpler.
yeah,
Um, they're not totally trivial to implement, even though they're quite well understood. They're still like a
yeah,
kind of tricky data structure.
yeah, they are.
Um,
Yeah.
and so here we then, what do we do here? We still need to take in snapshot into account. Um, you want to try and like write out code here, or what do you want to try and do right now? Um,
Yeah, like another angle, we could just open up a brand new file and like do it all in the B tree so that it can do snapshots and we don't worry about padding just yet. And then we can later make it indirect if we want to. So where we
hmm.
store some of the table info out of band,
Okay,
uh,
yeah, and just we store the whole table info inside the B tree for now.
like you were
Um,
saying like half an hour ago.
yeah, okay.
Yeah, yeah,
And so you just want to start, you could just get rolling in the B tree. Well, I feel like we should make sure we have the right API here first, that B tree makes that possible.
yeah.
Skid table is really all we need. Are we sure about that?
Yeah, if we can pass in key min, key max, level, snapshot, and get tables is just going to do everything inside it. Like it's going to find a table where the key range, the key intersects the key range.
Yep.
But then it's going to quickly check the created timestamp and deleted timestamp and maybe ignore the table and move on to the next table that intersects.
Yep.
Um, and that's our only requirement, right? There's nothing else.
I think so, yeah. It'll jump to like the right level, to get the right B tree, because we're gonna have one B tree per level essentially.
Yeah,
Other than that, we should be good. Um,
because then
yeah.
I'm wondering if the B tree shouldn't maybe just know about snapshot, key min, key max, and direction. So it's basically this interface.
Yeah, it could be that we just do the B tree. The manifest is just a B tree,
Yeah,
or 7 B trees.
exactly.
Um,
And internally the B tree can always use. You see, it's just a question of do we want to do like we want to do the indirection to solve padding. So some of the table info we store elsewhere. Um,
yeah.
but maybe it's just simpler if we do have a bit of padding and just put it all. But
Need to
but
start
but
with for sure. I think that's how
but what
we close the loop fat first, and then we come back and optimize the stuff if we find it's
exactly?
useful.
But
It may not
I
actually be that optimal, because then you have to do another lookup. I don't know.
exactly, and all bookkeeping overhead and complexity, and the other
Yeah.
thing too is that if we even if we do the indirection, it probably makes sense to do that within the B tree so that the interface of the B tree is very simple and you can always add the indirection later. It doesn't have to be on the side
Yeah.
of the abstraction. We should only ever go through the B tree abstraction. we shouldn't just think of the B tree as keys. It should be do everything for us. And how it's doing
Okay.
that internally with indirection or a separate array for the that's up to
All right.
the structure. You know?
Maybe we're going to call the B tree like level tree or something like that. I'm not sure. Like
Yeah, or like
level
Franken tree. Uh,
tree.
but I think a level tree is nice. That's perfect.
Cool.
Yeah.
Or level manifest. I don't know.
A
But I
level
think that should
tree.
be another file.
You know,
Level
another
tree.
file. Yeah, level tree is awesome name. Yeah.
A new file. Search lsm level tree. Type value.
Are you thinking to put
Well,
manifest in there so it's just a bit more clear that this is not the log LSM tree? This is something.
yeah, this is something else. Yeah, so like
Yeah,
I feel like I was thinking like level manifest
cool. That's
or something
perfect too.
like that, which
Yeah, that's better actually.
yeah. Value. Um so the key type, maybe we should just have like a table info type that's generic, then we can just like access the fields of the struct, which you always know will be there. I think this is what we want. Just have that one type here. And we'll
Okay.
access like table info.keymin and keymax inside
Yeah,
this function.
cool.
Then what else do we need like to be generic over?
It's only really the keys. Um,
Hmm?
yeah, only generic over the
Compare keys,
keys.
yeah.
Yeah.
So do you need the key type then as well? Might as well. You need the key type is to be able to find this function then.
Yeah, yeah. Nice.
Get all the things we need. Or your plate. All right.
um, and then we're going to have an iterator.
I wonder if this function, I guess this level manifest could just know about the timestamp stuff. There's a tiebreaker for this. If this returns equal, we'll just then go to the, we'll just look at table info that timestamp, I guess.
Yeah.
We don't need to encode that inside this function. Cool.
Yeah.
So I think we need, we'll need a const iterator. And the API will be similar to this, but not quite the same. Let's just copy this to get started though. It won't take a manifest. It's going to take a, just call it level maybe. Is like the struct for a level, right?
Yeah, that's it.
All right. And snapshot, it's good. Level is now gone. Keymin, keymax direction. Gotta get direction const.
Isaac, don't we need like a generics feature in Zig? Um,
Oh, sorry.
don't we need like generic types in Zig, like as a first class feature of the language?
You're making a joke now. we just return we just return types and functions.
Oh yeah.
Types are first class values. Just can't have
Sweet.
functions that return types, and that's how you get generics.
At
All
comp
runs at
time,
compile
right?
time.
At comp time, yeah.
Yep.
Okay, Cool. And but I think we do need macros in the language, surely. Like that's got to be coming.
Definitely not.
Otherwise, I won't use
Definitely
this language if it doesn't have macros.
not. Well, what do you want to do with your macros?
I just, create like macro types.
Just to make your code more or less readable?
Yeah,
Yeah, I see your goal.
just have this language that the other real language can never interact with, and they never the two shall meet. Yeah.
Good morning, Nipsey.
Hey, good morning. Nice. I'm glad it's
All right.
awesome. You've got have you got it going as RC, Isaac?
Yeah, I actually like did a Twitch stream doing like some river development on Saturday, and I got my IRC set up for that.
Hey,
And now I'm
sweet.
like into the Twitch IRC network, so I can just like connect to Tiger Beetle as well.
Awesome.
Yeah,
Yeah.
it's pretty nice. It's much nicer than having like the browser open with the Twitch stream while you're also streaming.
Yeah.
Um, a lot less bandwidth for sure.
And more,
Anyhow,
it like feels better. It's like much simpler to look at just seeing RC.
IRC is just
Yeah.
it's so much better than Discord, man, or like any other modern chat I've tried.
Yeah.
Um,
Yeah.
it's also like how I got into open source is just like talking to people on IRC, like because like all the open source maintainers are there,
Yeah.
and that's how you get like really high quality feedback on your ideas.
Yeah.
Um,
Yeah.
anyhow, we need to like put stuff in our iterator type and like figure out what we're doing here. Um, this is gonna need to change a lot as we actually implement the B tree, but we're just doing the interface for now, I guess.
Yeah.
Um, I'm not sure if I'm ready to just like implement a B tree on stream. To be honest, I need to like go read up the Wikipedia page. Um,
Oh well, may as well like read it together. I'm in the same boat as you, so we can just do
cool.
it as we like, just like we did the Eytzinger stuff. Because I mean,
Rebalancing.
that was
Yeah,
pretty
we
similar,
we stumbled through that pretty well.
Yeah.
Um, every node has the most m children, so we need an m, I guess. Every non-leaf node has at least m over 2 children. At least 2 children is not a leaf node. So the keys are always only in the leaves. Um, and then the nodes above the leaves just store pointers to multiple children. Um,
Yeah.
B tree. Yeah, so the nice part about them for like on disk layouts is they don't need to be rebalanced very often.
Yeah.
Um, kind of like how the segmented list works,
Yeah.
or the
And
unrolled linked list we were talking about works.
and that had the
Um,
same it had the same property where if we go up, there's five invariants here that make it a B tree at the
yeah,
top. The second one, that the unrolled has the same property that each node will
yeah,
have at least m over 2.
yeah. I think it's pretty much the same thing, but then it's just kind of flat instead of in a tree,
Yeah.
which makes it then not so optimal for searching.
Yeah.
Um, I think we might need a slight variant of this because we don't want to store the full values in the not in the non-leaf nodes. We just want to store pointers.
Yeah.
Um,
And I don't know what you think, but like, and we could do something in between the B tree and the unrolled, because we only have like 2 million tables.
yeah,
And I mean, we don't know which trees are going to be the biggest, but let's say like there's 4 trees that are big. So we've got at most 500,000 tables.
yeah,
And okay, a lot of them are going to be in the lower levels of the tree. So like levels 1 through, or level 0 all the way through
yeah. You're right. For level 0,
5.
so yeah, I think I've got a good way for us to think about this. A B tree is essentially just an unrolled list, but with um, a few nodes of indexes for this list to add like searching. essentially. And if we
Exactly.
don't need
Yeah.
indexes for the level 0, we shouldn't do a B tree. It should just be the unrolled list. And B plus tree is literally like an unrolled list, except with an index, because
Ex-
you then also store, like in the leaf nodes, you store a pointer to the next leaf node for better sequential
Yeah.
like iteration once you found the key you want to look up.
Yeah.
And we definitely want to do that as well.
Yeah.
Then otherwise you've got to go tree some pointers back to the parent, but
Exactly.
potentially going all the way back to the root to get to the next leaf node.
Yeah.
Um,
So what I was thinking is basically even in the bottom, like say we have 500,000 tables max, the B tree is actually giving you multiple levels of indexing to cut your search space. But we could do
yeah,
something, if it helps us think about it, we could do something like what we did for the block free set, where you have we actually only have two levels, one, the index level, and then the actual nodes. Because it might be that that's enough to get us good performance and it keeps it simple. We can reason about it. Uh,
yeah. I feel like just doing a B tree is just as simple, to be honest.
okay,
It's not that much different from doing one level.
but
Like
it
if you've got an index
means,
at all, then you might as well just do a proper tree, I feel like.
yeah,
Um,
yeah. I'm just wondering if we need it because we've got 500,000 tables max in the bottom level of the biggest tree.
okay.
So, like, how much index do we need for that? Maybe we need the tree. I'm with you. If we want to do it, then we do it. But
Yeah, and so I guess it's just how much we want to avoid doing linear scans.
mm,
Kind of the same thing as the Eytzinger layout. If we
yeah,
could use an Eytzinger layout here, that'd be cool.
yeah,
Um,
yeah. You see, we could even do like if I was seeing people were doing Eytzinger Layout for LSM trees, even where they just rebuild the Eytzinger Layout every because it's immutable once it's built. You can't modify it, you know.
right.
But since we're only adding tables every now and then when we compact, we could easily just like if our index is small enough, we can just quickly rebuild it. Um,
And building it in our case is ON because we have the layout
yeah,
done at compile time. And
yeah,
so it's not O log n or O n log n, just
yeah,
ON,
yeah.
which is pretty sweet. I think we should do that, yeah. I think that's better than the B tree index. I think we
So
want like
we
a segmented list, but then with like the Eytzinger layout to
as
then
an
index
index.
into this list.
Exactly, because that way
Um,
it's just so simple. Like you like with block preset, because DJ, we at first we were thinking we'll do two levels of index, and then we thought, well, actually we don't need it based on how much we address. We only need the top little bit of index, and then that's enough.
yeah.
Um,
Hmm.
do you want
Yeah,
to?
and
Do you,
so the tricky part becomes like how you get from the Eytzinger layout to the location in the in the unrolled linked list efficiently.
yeah,
I guess you still have to do like then. I guess the Eytzinger just lets you skip the first few point or index lookups in the unrolled linked list, which are ON. And so if we skip the first few of those, maybe it's fine to just do the unrolled linked list then.
yeah.
Um,
Do you want to pull up Python on your side, like to work double check?
I sure.
So we've got like max 2 million tables, and now we just want to figure out like how much index do we need?
Well, it's a kind of a fuzzy question. Um,
Yeah,
yeah, we don't really have any benchmarks, unfortunately, to like show us where the sweet spot would be.
yeah.
Um,
Well, we can kind of basically decide like, so we know that like one of the ideas that we used in the block preset was if we are going to do a cache miss to some random location, then the prefetcher can fetch 10 lines in parallel because the line fill buffer can fetch 10 lines at a time. So if we're going to jump somewhere, don't just read one cache line, read at least 10 cache lines because you get them all for the price of one.
okay, yeah.
So that's something to start with. So we know that we can do. 640 bytes per shard. And how many table infos can we put in 640 bytes? It's basically
That's a
10
good question.
if they're a
I think,
cache line.
yeah, they're 96 bytes, like if they're really big.
Yeah,
Um, yeah, like I guess it's like 7 to 10 roughly, I think.
yeah,
Maybe a bit more if you've got the 16-byte keys, but yeah.
yeah. The 16-byte keys are 96, but we don't use, most of the time our indexes, like the distribution is skewed towards smaller keys of 8 bytes or, yeah, so
Do they have 8-byte keys?
we
I guess we
do,
have the timestamps. Yeah, okay.
yeah,
Yeah.
so our table infos will mostly be 48 to 64, and some of them will be 96, but the weight will be, so we could use 64 as a,
Okay, yeah.
so
So 10 then,
yeah, so 2 million divided by 10, that'll tell
yeah.
us how,
200,000.
yeah,
Okay,
the
don't need
200.
to really type that in.
Oh, we just show our wiki.
We need units for these things. I
Yeah,
just want like a calculator that just like lets me write random units in here, just like show what the units are in the calculation. That'd be nice.
yeah,
It doesn't even use the units for anything. It just like lets you name your units.
and just ignores
Um,
it as like human
or could you even
stuff.
like just run with the units and then cancel them out. Like
Yeah,
we could just learn how to use arbitrary units. And
yeah,
so if you type in like 2 million tables divided by 10 or by 10 10 bytes per table info, then it'll give you like it'd be tables over bytes per table info or something like that. Something
yeah.
or like make up the units or compose the units for the output. So yeah,
To cancel them out is a killer idea, even if it doesn't know what they are.
exactly.
It's just, yeah.
You could still do that. I
Uh,
might do that at some point. I've got
you
like a
should,
Christmas break coming up, you know.
yeah,
I've already got so many plans of things I want to work on though.
you should call it like the Freund terminal, you know.
The friends.
I mean, that'll just be like the terminal to end all terminals. It'll be,
I don't know if it would be like an actual terminal. If you want just like a calculator, I guess.
yeah,
A
yeah,
calculator
okay.
app.
Yeah, yeah, it's just a calculator, but yeah, it's weird. I think of it as a
Yeah.
terminal, but it's not doing all of that. But
It's
yeah,
a REPL, like a read execute print loop.
yeah,
Um,
yeah. Read eval print. Yeah,
a read eval, is that what it is?
yeah,
Print loop.
yep,
Yeah.
yeah. No, that'll be so cool. So okay, so now we've got 200,000 shards, right, in our index. Each shard has 10.
Yep.
Um,
I think we just use the B tree. I think just using a tree is the right way to go here, like
yeah,
code wise.
because the B tree is going to
Um,
get it for us what we need and grow as much as it
exactly.
needs. It's going to keep itself
Exactly.
optimal. Yeah,
We can maybe optimize it slightly for our use case, but
yeah,
I mean that's just choosing M based on what our use case is, I think.
yeah.
Um,
But if we just to like just for fun, if we divide 2 million by 100, like say we have a shard which is like a page, so we'll get 100 infos.
you mean divide 200,000 by 100 or what?
No, 2 million by 100, so we'll end up with like 20,000.
Yeah.
Then 20,000 stuff in a key. That's kind of what we need in Eytzinger Layout.
20,000 what?
We need 20,000 stuff in Eytzinger Layout, like
Stuff.
20 stuff, yeah, like keys, key min, key max, um,
Okay.
in Eytzinger
Um,
Layout.
I
And
don't see a way to yeah, to go from the Eytzinger layout to the full array becomes a little tricky. Also, how to build the Eytzinger layout becomes tricky because you don't have like fast sequential well, I guess you got pretty fast sequential access, but you don't have fast random access. So the building Eytzinger layout also actually becomes ON, um, that's not ON squared. It's a lot slower than it would be otherwise. It's like ONK,
Hmm.
where N is the number of things in your Eytzinger layout and K is the number of things in your um, unrolled linked list thing.
Yeah,
Um, is to build the layout, you need to do point lookups. And so
yeah, yeah,
discounting it every time and rebuilding it becomes a bit more expensive. I think a B
yeah,
tree is probably better here because it just has to be, you just maintain it as you insert stuff.
yeah,
And you insert stuff through the B tree.
yeah. But I mean, the Eitzinger will give better lookup performance actually once it's built. And the cost of building it doesn't really matter because um, in the array-based layouts, they were saying even if your cost is, they gave you something like it has to be extremely, extremely expensive, but you're still going to win on the lookup speed. Uh,
Okay.
and we only do it when we compact tables. That's the only time. Um,
And so the Eitzinger layout will just like, how does this work? Did we just partition? I'm still like not really picturing how we get from the Eytzinger layout to. I guess we just need to rebuild it like every time we change the size of our list. Every time we append, or every time we modify the list, we need to rebuild the layout before we do the next query. Um,
yeah,
essentially.
and not even that bad. We only have to change it if, like, if the Eytzinger layout works off of the first key in each node in the unrolled linked list, then it's only if we add nodes or if a node's first key changes that we rebuild the Eytzinger.
Okay. Okay, so it's just gonna get us to the node then. Well, is that like a reasonable way to do that?
And maybe we want to put the min and max key of each node in the Eytzinger, but we can't do that. Eh?
No,
No.
Eytzinger just does it just starts based on one thing.
Yeah.
You can like append the keys together and use a different compare keys function if you want to take max into
Yeah.
account
Yeah.
somehow.
Yeah.
Yeah,
No,
yeah.
cool. But basically, yeah. So we only have to rebuild the Eytzinger if the first key in each node changes. That's it. Or if we add nodes. And it's not. That's only when we compact. Um, and the Eytzinger will be the optimal read performance. And then
To
we
remind
can,
ourselves what the API is here.
yeah,
We got search keys and search values. This returns a slice of values. We definitely need to change this API here to somehow return indexes, I guess. Actually, we could then use search keys, I think, maybe. Which then returns an upper bound index into the
yeah,
corresponding values. This is what we would use, yeah.
yeah.
And
Because,
yeah, and then we go from that index into our actual array.
yeah. And then, like, literally the node that we jump to, if that contains 10 table infos, then it's like a free, you get the 10 for free. Um, and that's it. So you do your Eitzinger search and jump to your table infos.
Okay.
You're getting 10 cache lines for the price of one cache miss. So you're getting them all for free. They're all in your CPU cache, and you just scan them to, well, they're all now contiguous. So you can even, I don't know, like they're sorted so we could binary search there even if we wanted to.
Probably, yeah. I think Eitzinger is the way to go over here. I think we probably want a pretty, we probably want to give the Eitzinger like a good bit of memory too to speed up, because binary search is a lot more expensive here than it is on contiguous arrays. And so we want to like not hit that case, that fallback very often,
Yeah,
or at least not have to do much binary searching at the end.
in our
This will give
nodes.
us, I
Yeah,
think this will give us be better than the B tree, I think. Um, the querying
yeah,
will be a lot faster,
yeah.
and
And
it's also simpler because we already have it done.
we have it
That's the
done.
other thing.
Yeah, because if we do the B tree, like it'll be a week, maybe 2 weeks of work to get it like tested.
I think we could do it a bit faster than that. I think we could get the
Yeah,
B tree. Yeah, I think we get a B tree done and tested in like 2 days or so. But there's no reason to do that. I think Eytzinger. Well, maybe that's too optimistic. I think we should just use the Eytzinger layout here. I think it's faster, and I think it
yeah,
also suits our use case nicely because
for
yeah,
lookups.
we still need to do the segmented list. But yeah, and then I was thinking there's probably like some ways to like make the lookups a bit faster there, like sequential like indexing essentially for the segmented list. I think you can like guess which node it would be at, but you still have to like that doesn't really work. You still have to iterate through the nodes to get there anyways.
Yeah.
Um,
What we need to do is make the nodes big enough. We don't want them to only have 10 things. We want them to have a lot more so that the unrolled linked list becomes more like a array. We
yep,
tune it so we
exactly.
make it very fast for iterating, um, which is fine, you know. Um,
Cool. I'm probably just like a little bit too worried about the performance there. I haven't actually used one of those in practice before, so I don't like, have a good feel for how performant they are.
yeah.
It's just all theory.
What we should think
Um,
of them like the name is actually misleading when it's called unrolled linked list. It's actually like a hybrid. It's a pure hybrid structure.
it,
Uh,
I think a
it,
segmentedly linked list sounds better.
yeah.
Also, what's that called? Maybe the PLF lib guy has got a good name for it. PLF lib.
Online they call it the canonical name is unrolled linked list
Yeah,
in all the articles, you know.
yeah. This is like the C++. This is like
Yeah,
a drop-in replacement for the std C++ linked list, which is just crazy fast in comparison, which
yeah,
basically just uses this property of doing a segmented linked list. He's got
yeah,
a pretty cool talk about this too. I watched a while ago.
yeah,
Um, he doesn't really have a good name for it though. Um,
yeah. It's basically a
but
ULL.
if we want to optimize this, we should look at his code. It's
Yeah,
very cool code.
yeah.
Um,
I've
it's
got
also like
just
way faster.
yeah. No, that's
Yeah.
cool. I've got an idea too. So we've got Eytzinger Layout. We don't, you see, for the ULL, or we call it a hybrid because it's either a linked list or it's an array. It's one or it's on the spectrum, so you can tune it. Um, the name is actually misleading, you know, like so
Mhm.
for a hybrid structure, those nodes they contain next and previous pointers. They also contain the count of how many elements are in the node.
Yep.
Um, but what the trick is, what we do is we take that metadata and store it out of band contiguously.
Oh, cool. Yeah, I like that. That's nice.
Because
And then we have like, well,
that way we can iterate that whole thing like super fast because we'll go from Eitzinger, then we want to get like the 100th element. So now we've got our contiguous pointers. We can just scan that linearly to jump straight to the node instead of doing a few jumps. I don't know. Maybe
yeah.
that's
Then
overkill
we need
though.
more memory though. That's essentially then doing a B tree.
Well,
Or
not
kind of.
really. It's just that we will need a little bit more static allocation, but it'll be
Yeah, well,
better
we
than
need
the
like,
B tree
yeah, it's not really a B tree. It's something a little bit different from that, but
because
yeah.
we're storing all our pointers all contiguously because we can work out
Yeah.
the max.
So basically, it's kind of like storing, yeah, you store your nodes in a contiguous buffer, and then you have like the actual buffers of keys is what gets allocated by the block. And so we still have the same like like pool of buffers that this linked list is backed by. But
Yeah,
then instead of like putting the node information and the data in the same buffer, we use
please.
like one buffer. We fill that up with node informations, and do a linked
Yeah.
list there, like the linked list index, and then each node has got its own pointer to a block, or actually stores many pointers to a block. I think. Yeah, I'm with you there. That sounds really good.
So we do like
Um,
structive arrays where, yeah, instead of like meter and data in a node, we split it out. So the meters, but we want
let's
the
write this
meter
out real quick.
to be contiguous.
Um,
Yeah. We can even use two unrolled linked lists, like one, oh no, we can't, because, yeah, but anyway,
so
Yeah.
here we can just store, it's just a slice. Just a slice of, I don't know, I'm just gonna call it T for now. This
Yeah.
is like not the right name for anything anymore.
Yeah.
Um,
Cool.
Let me just delete this. I
I,
just want to delete this.
I think
Yeah.
keep. Yeah. Okay.
Maybe we should keep it because we should probably do the
Yeah.
Eytzinger layout like in here and like abstract that a little bit.
Exactly. This is going to be our big thing that like abstracts it, hides it all away, whether it's a B tree or
Yeah.
whatever it is. Yeah.
So we have this node thing, and this stores just a slice of data. I think it's just a pointer to the data and then the length, and then
Yeah.
we can know that it's actually a bit longer because we'll have like a comp time known like block size essentially for this list,
Yeah.
or slight or like unit of
It's actually
memory that we
just
use for this stuff.
it's actually just a zig slice, the pointer and the length
Yeah,
of the node.
that's all the. So we just store like a slice of slices,
Yeah.
and then each slice is like a segment in our list, and then we fill out one of our chunks of memory we fill up with just slices, and that's then like our index.
Yeah.
And then we also need a pointer to the next slice of slices in the previous. We need prev.
And I was thinking we actually only need one, and then we do the XOR trick on this. So we don't need to store next
Sorry,
and
what?
previous. We
We store.
we do the XOR trick, so we only need one pointer. But
That
then
doesn't
we
usually
don't.
help us though with padding. With padding, that doesn't really buy us anything.
It
Um,
it just means that our metadata array, we only have to store a pointer to the node and
oh, we're doing structured
length.
arrays there, then maybe. Yes.
Yeah, yeah.
Uh,
But
well, still, I don't think it buys us anything.
we
Maybe a
want.
little bit.
Okay, yeah. So you want to do next pointer, previous pointer, and count.
Um, no, we actually can't. Well, I think we maybe can we even do that with the XOR trick? I think we want next and previous pointers though.
Yeah.
Um,
Okay.
well,
Because I
it's
mean,
not.
i we could do the XOR trick if we just store the tail pointer and the head pointer. Then, depending on direction, we just and actually maybe it's easier that way to make our direction stuff work.
Let, let's come back to that after we've
Yeah.
got like the rest of the design. That's optimization. That's not design.
Yeah.
Um,
Yeah. Yeah. But maybe it makes the design nicer and easier. Like I'm just saying, you know.
maybe we'll
Yeah.
see.
Yeah.
Um, this is like an index node. I think that's what I'm
A-
gonna call it. Index
Am I
node.
overflowing our stack? Um,
Yeah, exactly. Um,
cool.
it's
Nice.
optional. They might be null. Um, then we've got, well, maybe we can see what we want there. We might not make them nullable actually. We might like use a ring-based linked list.
Yeah.
Um,
Cool.
then this index node then has a slice of slices as the data inside the node. And yeah, that's it then.
Yeah, it'll actually just have one
Well,
slice. Just the node has got just a slice, a pointer and a length. That's it.
what?
The node only has a single slice of data.
Yeah, well, this thing is like stored inside a slice, I feel like. So maybe this is the wrong way to have this type. I think like well, there's just gonna be like data entries after this in memory. Every entry is gonna be a slice then.
Yeah. Before we use this type, just above where we define const iterator, we just do the actual fixed array and
What do you mean by the fixed array?
okay. Well, basically it'll be like meter, and then we'll give it like a thousand, a thousand um, node metadata types in the array. So, because basically what we want is the the node metadatas, they must all be stored continuously.
Yeah, that's what I was kind of trying to do here.
Yeah,
You've got a previous pointer to the next block of metadata, a next pointer to the next block of metadata. Then after these two pointers, you've got just slices, and each slice is then a slice of data. Um,
yeah,
does that make any sense?
yeah. I think uh, it does, but I was thinking like, what if we just have a fixed array, and in the array we don't have to store the previous and next pointers at all because you increment your
Well,
array
what
index.
if you have more things that you can index with that array though? It doesn't
Exactly.
scale to infinite list sizes.
And that
That's why you need a linked list of these things in
a
as
linked
well.
list of arrays, right?
Yeah, that's what
Okay,
the previous and
thanks.
next are here.
Yeah, okay, cool. Now I
Um,
understand. Yeah.
cool. And then I'm not sure what the API for this is yet because it's actually backed by a single buffer. We want to like have then, I guess we just have an array is what it is. It's then we have then data, an array of slices. Um,
So these are actually
it's like
nodes. It's an array of
yeah,
nodes. Okay.
and node is just a typed up for a slice, I guess.
Yeah.
Just do that just for currently.
Cool.
Whoops. And 10 is also wrong. Let's have like a constant for our
Yeah.
const for like the size we need for
It it'll basically our index node, we will allocate it also just using our pool allocator. So it will be
exactly,
like
yeah,
we can call it
exactly.
page size or line
Page size.
size, page size, and we make it like
I don't
4096.
know. For chunk size?
Yeah.
I kinda wanna call them chunk.
Okay.
Is that good?
Yeah.
That's
I
your
yeah.
segment? I don't know.
Cool. Chunk is cool.
I think pages is not really that that seems like a different kind of concept.
Yeah.
Block we could I would usually use like block size, but we've already got that for the rest of for the on disk stuff.
Yeah.
Um, I'm just gonna choose a number for now. I don't really doesn't really matter what it is to do.
Or Isaac, what do you think of just calling it node size 4096 in bytes?
Sure.
Okay.
And this is then not 10, but node size minus 2
Times.
times size of index node, um, and also divided by the size of a data node.
Yeah. Nice. Cool.
And then we need to then like make this an extern struct, and then do some content search in the size. Size of index node, node size. All right, that's feeling better.
Cool.
Cool. And then the data node, yeah, so I think we just use the slice. We know that we can slice up to node size essentially. We'll have another variable here for like the actual number of elements in that are in here then.
Yeah.
Um, yeah,
Nice.
this seems good. We could also, hmm, actually, I'm not sure if this actually works in Zeng because we don't have a well-defined memory layout for extern structs.
Yeah.
Actually, we can save memory here too because we make the struct of arrays and use U32s instead of lengths, instead of U sizes for the lengths.
Yeah. Yeah.
Um,
Great idea.
um,
Perfect.
how much memory? Can we actually save that much memory? I think we get like one more pointer or something. I'm not sure. Um, so we essentially make so data or child child pointers or children, and we got like children lengths maybe. Children length. We also need to know how many children are stored in this node in particular. We
Yeah,
need like children
the
count
count.
as well.
Yeah.
And then we need children children count or child count. I think is better.
Yeah. Yeah.
Child
I
count.
I like node even better, like node count.
That seems confusing because we're calling these ones nodes too.
Okay.
Um, we could call it like data node count if you like that
Yeah,
more.
yeah, that's cool. Data node count, data node um,
Pointers.
pointers, yeah. And then,
And then this needs to be updated. It's just a pointer. Um, pointer to T, I guess. And T is table info actually, I guess.
yeah,
Is that what this is?
yep.
Yeah.
And then, are we both thinking that data node count, that is an array of U32s or a slice of U32s where it
No.
base.
This is the number of data node pointers that we have inside this index node.
Okay, cool,
Because
cool.
this is gonna be like to do
Yeah,
length. So this is gonna be an array here. We need to know how many are in use currently. Um,
cool. And for each, we also need to store for each table info, or not for each table info, but for each data node, how many
how many
elements are in that node so that we can skip over
exactly?
nodes
Yeah.
as we to
We
look
don't have
up.
to access the memory. Yeah,
Exactly.
exactly.
Yeah. Yeah.
The data node um, lengths,
Yeah.
pointers, count. So now we need to figure out how to make this fit the right memory size for the cert.
Mm. Maybe,
Um,
maybe we should call, instead of data node lengths, call it data node elements. It'll tell you how many elements are in a, and it lines
like
up.
that.
Uh,
I know you
yeah,
count the characters there.
I
Um,
did. Yeah. Yeah.
All right, cool. That definitely looks nicer.
Yeah.
Um, I'm tempted to do the XOR trick now, so we get rid of this U32 essentially. But we
Yeah.
can come back to that later.
Cool.
I've always wanted to use that for something real.
Yeah. 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 Because it's nice. Then when we start the loop, we make our branch there to decide on our direction. But from then on,
Yep.
we just XORing into a single field. We're not switching which field we use. We just use the same field, just XOR.
Yeah.
Oh,
I think it could actually be quite nice for this. Yeah.
yeah,
We'll come back to that for sure.
yeah, cool.
And then we maybe, hmm, I'm thinking whether we want to use null. I think we don't use null to indicate the end of the loop. We just then have it be a circular linked list. So then
Yeah,
the last pointer is then also. So we have here like in level map. So we've got head and tail.
head and tail.
Um,
Yeah,
head, which is I guess these would be optional then maybe. Um, no,
yeah,
because we did these also are not optional. They just point to each other. Or they point.
yeah. Because
Well,
there will always be at least one node, even if it's empty.
yes, yeah, sure. And then tail, they'll be the same node if the linked list is empty.
Yeah,
And then the previous and next will this will just point to um yeah, so this will just point to itself, I guess. We'll have one here, so we have just some pointer or what do we call this? Just like
We
Link.
could, yeah, link is cool.
I think link is good. Oops.
Mm.
This should be a U size,
Yeah.
I think. It's like it's not an actual valid pointer, so we shouldn't
Yeah.
just make it a pointer. We
No.
need to actually, yeah,
Yeah. Maybe we must just define an unsafe, put this in an unsafe block or not.
an unsafe block.
Yeah.
Maybe if we
Or
were using a different language, we might have to. But Zig lets us do this stuff if we want to have fun.
yeah,
Um,
cool. And then we're just going to use, yeah, pointer to int to pointer.
exactly.
Mm.
What we'll do, well, next thing this will look like we take the if we want to go forward, so we're gonna take head. We'll follow that pointer. And we're gonna XOR the pointer to this struct itself with the link of the struct. That'll
Yeah.
then give us does that only work for one directional iteration? Can you actually go both ways with this trick?
Yep. Yeah, you just put in your head or your tail as you're starting.
Okay. And so you don't XOR this with the link that with we XOR this with like the pointer to the struct itself. And then I'm forgetting exactly how the details of this work out.
Yeah.
Um,
We can look that up quickly. XOR linked list.
the Donald Knuth.
Yep.
Yeah, it's A and C. That's what it is. It's not the pointer to B. It's rather the pointer
To both
B
neighbors.
and C. That makes sense. Um,
Hey, and they call it link as well.
it's the right name for it.
Yep. So it's just if
Yeah,
we
but
check, it's just the pointer to the two neighbors. It's the pointer to each neighbor XORed.
yep. Except if we only have one node, then there are no neighbors. And so what is this then? This is
What do they do in Wikipedia? Do they show
I
that in
think what we need.
HBase?
Well, I think it's probably a circular linked list, isn't it?
Yeah.
Um, mm, oh, at address 0. That makes sense. Okay. Link at field A would be 0 or B. And so if there's only one node, it would just be 0
Yeah.
here.
Okay.
We kind of use 0 as the first to indicate like the head and the tail. And
Yeah.
so we start off with just 0, indicating the first element. And then when we add one element here, then we XOR 0 with that element's address to attain this link.
Yeah.
And for the new element, we XOR this element's address with 0 to maintain the second link.
Yeah.
I think I'm cool with
That's
that now.
okay. And are you happy that it's more ergonomic like this actually to do bidirectional based on a direction? You happy with the
Not totally convinced on that, but I think it's
yeah.
not bad. I think it's fine.
Okay.
Um,
And
I think
you
you're right. There'll be less branchy. I think
mm,
you'll always just start and then you'll iterate. Well, yeah, you'll iterate the same. You'll use the same field no matter which direction you're iterating, so it'll be the same code essentially.
the same
So
code
that'll be
path.
nice.
Yeah.
You just start at a different either head or tail in the iteration
Yeah.
function based on the direction. Yeah,
Yeah.
that's cool. But then no, because that's not actually going to save us much because we still need a branch to know which way to go through data nodes by. Um, you have to go
Okay.
through data nodes in some direction, and so there's going to be a branch there.
Of course. Yeah. Well, what to avoid the branch, you can actually have a direction like a sign um, that we add into our calculation, you know?
Like a, what do you mean?
Um,
Like a,
you, you just do it in terms of arithmetic.
okay, I'm sure you can avoid the branch in the code somehow, but we'll need to have like two code paths there essentially,
Yeah.
even if there's no actual branch.
I was even thinking just one code path there too, but you express the direction in terms of the arithmetic. So
Right,
you would
but then you still need what we need to like start at one end. So we like pass in like a start and and a direction and a sign.
exactly. Yeah,
And
that yeah.
well, the start also we still need a branch thing because we need to know the count based on the node. So either start at count or you start at 0. And we can't like pass in the. I think we should not worry about that too much.
No,
Um,
we
I'm
can do
fine
that
doing this trick.
later.
I think it's safe.
Yeah.
We should now do the math to figure out this to-do length though.
Yeah.
Maybe this needs to be calculated at comp time, or maybe it just
Yeah.
makes it. We're gonna take node size minus these two things, and we kind of need to solve an equation here. The equation is, let's just write it out here, I guess. Um, so this is like element count or data node count.
Yeah.
No, or data node count max. Max equals node size. Well, let's just call it what we have here is x equals node size minus um,
Size of
size
U
of
size,
link plus size
size of data node
of
count.
data node count.
And it's actually, we need to
Okay.
use minus there. So it's minus, unless we do parentheses.
There, yeah.
Minus is nice. Yeah.
I was gonna do parentheses. I had parentheses in my head, so I'll just do them like that. I think it's better that way.
Okay.
We're gonna take x, and well, I guess these things are twice as big as the other ones, and so we're gonna divide it in 3, I guess. So x divided by 3, um, is the data node. No, divide by 3 times 2. So that's then the data node count max. Are you with me there? Um,
I'm catching up.
um,
Uh, I,
these things are twice as big as these things, right?
the
And so now
pointer.
we've got
Yeah.
essentially we can think of it as like 3 arrays of this size, where we use 2 of the arrays to do this part.
Yeah. Yeah.
And so if you
Yeah.
divide in 3, you get 3 arrays of this size,
Yeah.
and then you can use one of them for that and use 2 of them for this. That's
Yeah.
how I think about it at least.
Yeah.
Um,
That's awesome. Cool. Then maybe we must just express the ratio as the size of the actual types in case the U size
yeah,
changes.
we definitely should do that. This is
Uh,
then this is the size of,
U size.
yeah,
So size of youth.
okay. This is then the size of both of them together. And then,
The smaller one. 2 over
yeah,
3. Yeah, the size of the smaller one. So we'll need like to work out between the U32 and the pointer. The main is that a many pointer? That
yeah, it's just a pointer to multiple items, an unknown number of
yeah,
items.
yeah.
think this is actually right. It's just to use U32. Then you get the size. This is then the size of this
Yeah,
array divided by the size of the 3 arrays. And so
yeah,
that'll give you then,
that's fine. Then we just have to assert
well,
that the size of the U32 is
this is now,
always less than or equal to
this is
size of the many pointer.
1/3.
Yeah,
This what I've got highlighted is just 1/3. That's what it is.
yeah.
Um,
Now it must be two
this X,
times size of U32, right? To get 2 over 3.
is that actually right there? What I said earlier. We want to divide this area into 3 to find. It'll give us the size of the area. We not the actual count. That's the difference. Okay. This is now the size we want for this array. Then we need to divide it by size of U32 to find the count.
Yeah,
That's what the thing is.
yeah,
We need to take this and divide by U32. So this is the data node elements size, and then size. I should do now. Let's do this in comp time and put it up top.
yeah,
Cool. So we want to have here, or I guess we can not do it at comp time. Instead, rather, let's move this around like a little bit and have here just const data node elements count max. We'll just do this in a block essentially. And here we're going to do I'm just use X for now, just like basically copy this.
yeah.
Put in actual code now. We got figured out.
Isaac, just to check if I understand, data node element
Yep.
size, we we're saying that it's x times 1/3. That's right. That's what we're looking for there.
Yeah.
X times 1/3. Yeah.
Yep.
Okay. And then
And we could also do 2/3 and then divide by size of this pointer instead. You get the same result in the end, I think. As long as there's no rounding errors. That's the only part I'm worried about now.
yeah,
If
me
we
too.
have,
Yeah.
yeah. But we have this assert here that would then tell us if we ended up with padding.
Yeah. What we should do also is say we should assert that the size of U32 is always less than or equal to the size of the many pointer or pointer to many. Because I mean, it's never going to happen. But if it did, then we would have to flip our ratio around so that we do
Whoops.
the numerator. At the moment, we
Or we
assume
get
that
actually a
U32
compile
is
error if that happens already, because we divide by 0, which is illegal at compile time. Or never
no,
mind. But we got the
no, no.
assert now. It's
But
fine.
the assert is actually less than or equal to, because what
I was
our
gonna do
ratio.
just I was gonna say it's equal. I was gonna do this. It's
Okay,
exactly
cool.
twice. Yeah.
We don't need to do that. I think it's all we need to do is because you see our ratio, we're trying to put the numerator needs to be the smaller type.
Yeah, but this is like more restrictive, and I think this is just easier to reason with. This
Yeah.
is what the truth is, and we just want to make sure that the pointers are 64 bytes on this
Okay.
architecture we're targeting, and then we're
Okay.
fine. So I think
So
this is. I want
target
to make things
wheels.
as
Yeah.
concrete as possible, make it
Yeah.
easier to understand.
It just
This is
that's
now.
cool. We won't work with bigger pointers then. That's fine. Yeah.
Yeah, we'll certainly need to update stuff if we ever end up with 128-bit pointers, which I don't think we will because
Yeah.
CPUs don't even use the full 64 bits. They only use like 40 some of the fits.
Yeah. I think that I'm not so happy though with this because if we do a 32-bit build, I know like some stuff won't work, but then this will break straight away. This will prevent a 32-bit build.
Do we really, does that really work? Like, don't we need like more than 4 GB of memory?
Not necessarily. Like that'll be bounds
Okay.
checking that will check that.
I mean, you can also just use the U64 here, instead of a U size for our link.
That's maybe better,
But for here,
Yeah, there we need it. But I think what because you see for this stuff that we're working on, all we're trying to do what you see we've assumed that U32 is the minimum type, so that's all we want the assert to check. Uh, just that the U32 is less than or equal to the many pointer, then it's fine. And then we could add another assert
yeah,
to make it concrete and make sure, because I think what we're trying to do is also check that we don't have the rounding errors. So we could just assert that separately,
well,
and then
this
that's
assert does.
okay. But that's a good one to have. But for our ratio stuff, right where the ratio stuff happens, we should also check that um, either the U32 and table info are the same size, or they're multiples of each other, so that our ratio stuff is easy. Okay, no, but that doesn't work actually. It doesn't help us. Okay, cool.
I think this is fine.
Okay, but we must just change the assert then to be size of use32 is less than equal to.
It's really necessary.
Yeah, because you see, if you look at our ratio, our function, our fraction that we take,
Yeah.
that logically there, what we're really trying to do is ask ourselves, which is the minimum type
No, we
uh,
don't care which type we use here.
as the numerator.
No,
Ah,
all
okay.
it needs to do is, we only care that this type here is the same one we use here.
So if we use the bigger type, would that be fine?
We just have to use the bigger type here as well. It would also be fine to do this. Um, not that. That would work just fine.
Oh, okay, cool. Sorry, I misunderstood. So then we don't need that assert at all. Uh,
Yeah. Probably clean this code up a little bit. Um,
yeah,
what should
that's
X be called? We need a better name for this one. It's like link
um, just like
or
Professor
metadata
X.
size.
Professor X.
Size. Um, this is wrong. This is node size. Oh well, let's just do like this. Let's do metadata size is this, and then here we're gonna do like node size minus metadata size
And then
times
rate times ratio. Uh, Okay.
well, integer division makes if we do the ratio separately, then integer division kind of messes things up. We
Yeah,
don't want
yeah,
to do that.
yeah.
We want to do it like this, really.
Cool.
I think this is fine. This is like a little bit
But
unreadable.
no,
It's
it's
readable
cool.
enough, I think.
Yeah.
Um, yeah. Anyhow, data
That's
node elements count max.
what we could do is we could have um if you like yeah, I don't know. It doesn't work. You see, I was thinking we could have constant numerator, and then we use the numerator in the same, wherever we use it. But in one case, it's the numerator, in the others is actually the denominator. So then it looks even more confusing.
I think we should just
Yeah,
keep it like this. This is nice and
yeah,
concrete, I think.
yeah,
And then we can move this content assert up to like just show that this is what
yeah,
we're trying to go for.
yeah. Cool. What do you think of doing, instead of metadata size, we just have remaining, like remaining size, and that way our
And
ratio gets cleaned up nicely. We've got less stuff
then, okay, we can
happening.
do that. Yeah.
Cool.
And here we are. Still gonna be kind of long. It doesn't fit in one line.
Okay.
Still
And
better like that.
if we do just remaining, does that work or not?
Still gonna be 114 characters.
Yeah.
We can also make this shorter.
Yeah.
104. Getting there. We have like a typedef for pointer size. Use it here as well. How's that?
Oh, that's cool.
It does get a lot more readable when you have like smaller variables and less noise.
Yeah. Yeah. It's good.
Then we've got a nice long variable name like outside the block.
Yeah.
And yeah, cool. That seems good to me. Now does this actually work out with I think we're in a padding here because we end up with like a U32 here now
Yeah.
instead of, so it's gonna be like we can just Python it out, right?
Yep. Awesome. We could also just make that node count to U64, a U size.
Yeah, we could do. That's probably the best way, the simplest way to get rid of the padding. Yeah.
Yeah.
Um,
Make it a
and
U
here we've then
size.
got like 4096. If we use that minus
8.
64 plus, or let's assume it's a 64 now to see if it actually works out.
Yeah.
Then we've got 36. We can also make it a U size. That's another good point because then it would actually work out in 32 bytes as well, I think.
Yeah. That's what I was
Yeah,
thinking. Yeah. Cool.
nice. Let's try for at 64 bits first. Then we got 3968
It should actually
is
be,
now
instead of
remaining.
64, we should have 8 and 8, because we're mixing up bits and bytes.
Sorry, what? Oh, 8 and
We
8.
8 and 8, yeah.
Yeah. Yep. I'm gonna use variables now because why not? It's Python.
Yeah.
Um, Size equals times
4
4
over 12.
over 12. It's 8 plus 4, yep. And then
Element size
times
over 4.
340. All right.
Yeah.
That's our data node elements count max. Now let's do the full size. So we now got 8 plus 8 plus 340 times 8 plus 340 times 4. Looks good.
Sweet. Hey, awesome
You
insight
know,
on
Python,
that
I should start doing this more
on that
often where we use variables for
ratio.
a calculator.
Yeah.
That was really nice, I found. And you could like,
Yeah.
yeah. cool.
Nice. Yeah, awesome. I like that insight of yours to do the ratios, like fantastic, you know.
Thank you.
Yeah. You think it's a good
All
time
right.
for a,
So,
shall we take a 5 minute break? What's the
sure.
time?
It's 11:32 on my side.
Okay.
Yep. Your
Do you
break.
want do you want to keep going and do lunch, or do you want to do a quick break, then keep going and do lunch?
We keep going and then do lunch in like half an hour or so. I don't know. What are you thinking?
I think so. Let's keep going. Yeah. Cool.
Cool. Um, cool. All right. And then on should we try 32 bytes as well just to make sure it works out?
Yeah, yeah. While
Um,
you do that, I just want
okay.
to fetch something to show you.
Go
I'll
for
be
it.
back in a second. Uh, so now I too am one with the tiger beetle.
I've done mine.
Hey, really? Cheers. Yay.
It's a little weird on stream to have like shade over my face though.
Oh yeah, and we've actually got a whole like tiger beetle costume now.
Oh, you guys got shirts too already? Sweet.
Yeah, yeah, it's coming to you as well.
I should have a hat and sticker.
Yeah. So
Nice.
and also another one, which is
Oh,
pretty
nice.
pretty good for
That's the
tiger beetle
coolest one.
sessions, you know. Yeah. Thanks,
Yeah.
Joey Max. Yeah,
Oh yeah. Cool.
yeah,
So much swag.
yeah. Nice. Martin Thompson liked that viewstamp replication is the not only the first consensus protocol to tolerate network partitions, but also the first consensus protocol to have its own swag. he
There's
he liked it.
no raft swag? I find
So
that hard to believe somehow.
sorry,
Um,
Isaac.
there's no raft swag. Um,
I don't I don't think so. That's why I asked them. Like I asked everybody, so now they can confirm. Like if it's true. I believe that it is not only the first. Uh,
times times 4 divided by 4 plus 4. Ooh,
Nipsey says sick shirt. Uh,
thank you.
uh,
Element size 2044, and then we do 2044. Um, element size divided by 4. Then our total size is going to be 4 plus count times 4 plus count. It's gotta go in evenly. Yeah, of course it works. Cool.
awesome.
You were frozen for me.
You
You
were
or
frozen.
you, you or 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 you or
Hey, Isaac.
hey, I think
Cool,
we're
we're
back
back.
now.
Yeah, yeah, we're back. Great. Okay, Knipsey says, yeah, we're back.
Right.
Yeah,
Cool. Nice. Cool. Well, back
uh,
into it then. I think we've got our index node
yeah,
struct worked out, and we'll just kind of
yeah,
bitcast the buffer into this struct,
yeah,
um, or pointer cast it or whatever.
yeah.
Anyhow, then
By,
we
by the,
have
by the way, I think Nipsey, we don't have your address, right? Uh, maybe you need to get in touch with Isaac or I, like out of band, um, so we can do like a take a pointer to Nipsey's address,
maybe.
if you know what I mean. Yeah. Yeah.
If he says, "Wow," we've got a swag now, right? Um, cool. So we got data pointers and whatnot, and index node. Cool. Iterator. This iterator is very, very lame currently. Where are we on to now? I think we've got our layout, our data
Yeah.
layout done.
Yeah.
We should put, maybe like make sure iteration over these links works out like we think it does with like this XOR nonsense. Um,
We don't have to do it,
but
we can just do previous next
it is
pointers.
actually nice though because we get one more data. It is helping us because we get one more
Yeah.
data element per index node because then the count
Yeah.
fits in the space there, which is
Exactly. Yeah.
pretty sweet. Very happy we found like a good use case
Mm.
for this.
Yeah.
Cool.
Cool.
Um, maybe we should just like do some basic like get node at index operations and like implement those and see how they work.
And get it
Um,
compiling and that. Yeah.
yeah, I'm gonna put this one like up before the fields here. I think this looks better
Yeah.
there. We've got
Yep.
like the for the actual struct, and we've got like um get. We just like take an index here. Um, this will return table info, I guess. This is just we might not end up using this long term. I just wanted to like just do this to see how we would do the code.
Yeah.
We
Cool.
probably want a
Awesome.
different API longer term, but this will get
Yeah.
us started, and we'll
Yeah.
probably reuse whatever code we write here too. And
Yeah.
so what we're gonna do is just say like var I equals 0, and then we're gonna start iterating through our nodes and incrementing I until we get to the node where index is essentially.
Yeah.
And to know the total number of nodes at each level, we might want to take this back down to a U32, because, or maybe not. I guess math is probably cheap actually, but we need to like iterate this whole array and add all these U32s together.
Yeah.
Um, get the total number of data of table infos per index node. We could cache that in a second U32 inside the 64 bits of memory. Um,
I
I think that might be better.
I'm not with you on that.
Okay. Um, so to iterate past an index node, if say the index we're looking for is not in the first index node, but in the second one,
Yeah.
to know that it's not in the first index node, we need to add together all these element counts to know
Of
how many
course. Of
elements are in
course.
the first node.
Yeah. Yeah.
And so it might be nice to cache that here to divide this into two U32s and cache that here.
Yeah. No,
Um,
that's excellent. Like that's where this thing really shines because it's now it's like hyper accelerated because you don't even need to go like
node,
you know,
yeah, your index, your total. So let's put this actually first, or maybe total elements.
or elements count. Yeah, total elements total. I
Yeah, I think that's
or
we want this first too, because then this is related to these ones,
yeah,
and padding works out nicely still. That seems good.
yeah.
Cool.
Do you want to
And
do
so
total or elements count? Is elements count okay?
I think total um
Yeah,
is good. Then
yeah,
it's node the elements total, and then you can
yeah,
see if the index is less than that, then you need to go.
yeah.
Well, that only is like for the fast path for skipping things though. If it ends up being inside this node, then we still need to go iterate through the elements array and
Exactly.
go.
Yeah.
Yeah, maybe this isn't worth it then. I'm not sure.
I
Um,
think I think it is because if you definitely not in this node, that just helps you know
yeah.
straight away. We
I'm
could
also wondering how many of these nodes we're gonna have because I think we're not gonna have very many of them. Um, we might
yeah.
want to work that out at some point. But if each of these stores, I guess we had 300. Well, for 4096, which is 4 kilobytes, which is what we were kind of thinking
Mm,
might be good. We're gonna have 340 of these, I think.
yeah.
And each of those will have 4096 divided by table info size table infos. Um, that's gonna be
Okay.
quite a lot of table infos, but maybe it's not gonna be enough. It's not millions. We're gonna need more of these to have millions, I think. We're going to have a lot.
So, well, so 340 times 496 divided by 64, that gives you 21,000 table infos.
Yeah, so we will have several of these nodes. I think the fast path is definitely good to have. Um,
I'm not sure though, like if you've got, say we've got 21,000 nodes for 340. So say we now have four index nodes
yeah,
or two or three index nodes, or actually 10, then we're already at 200,000. But if we're iterating 10 nodes, it's actually quicker to just make it branchless, not even worry. Just always
okay.
iter it across. Uh, I don't know what you think.
I think
Or
I buy that. Yeah, because this is only iterating. This is like literally iterating 340 U32s and adding them together. That's pretty fast. Like there's not many things you can do that are faster than that. If it's then linear, I guess it comes up like we've got 10 nodes, then it's 3,400. Um,
yeah,
that's just iterating
eh,
over, and that's the worst case. Like if it things at the very end.
yeah.
Um,
Actually, maybe on second thought, I think I'm getting. You see, I was mixing stuff up in my mind. I thought we've only got a few index nodes, like four or five, so don't branch. But actually, if we do have this elements total, it saves us from 340 iterations, which is quite significant. Plus, plus what helps is that we don't need to do the cache misses to go into that. We're just loading the first line of the index
yeah,
node and then we
that's
jump.
right. So let's go with it for now then, and then now we've broken
Yeah,
it for U32 for 32-bit pointers, but that's fine maybe. Um,
that's fine.
Not sure what the
But
solution is there. I think we shouldn't really care about 32-bit architectures yet, though. That's
yeah,
pretty easy
but
to retrofit, I think. We
how
won't
does
be as
this?
optimal potentially, but yeah.
Okay, so
Anyhow,
this for 32-bit, this breaks our assertion, right?
yeah, because
Um,
now we've got yeah. Now we end up with an extra 4 bytes of padding essentially.
yeah,
But we could solve that by making link a U64.
yeah, which um, which is good.
So,
Let's do that then.
all right, I think my internet's being bad now. Can you still hear
Okay.
me?
Yeah, I can still hear you and your video is coming through fine. I don't know if you want to
All
just
right,
move
cool.
move your mouse just to check your screen share. There we go.
Cool.
You're coming through fine.
It seems to
So
be back now. It's just like it's being a little bit unstable.
yeah,
Um, We'll see. I lost a bit of what you said though, I think. But I think we make this a U64, then we work out for 32 bytes.
yeah,
Um,
That's fine.
Cool. Though, then we need an int cast for the pointer to int to make it compile in 32 byte architectures. I'm not sure about that. That seems kind of weird to do.
Yeah.
I
Shall we just
feel like
say
we should.
that, are we going to then make it across the whole of Tiger Beetle that it doesn't run on 32-bit?
I'd honestly be fine with that.
Yeah.
At least for our current iteration of Tiger Beetle, I think we can add that, in retrofit that pretty easily. But that's just like an extra time sink that we don't really need to get to production release. I don't think, because no one's gonna run this on production on a 32-bit server. That'd be more for like an accessibility thing for um like more like off the grid uses of Tiger Beetle. I think we want to support. I'm totally all for supporting that stuff. Um,
Yeah.
but
We don't have many,
yeah,
we have very few places where, I don't think we have any places where we prevent 32-bit use, you know?
yeah. I don't think we should support it without testing it. I think we would need then CI to test it on a 32-bit machine.
Yeah, no,
Otherwise,
that's,
we
yeah,
can't support it. I think we should have an assert until we have a CI that tests it and we've actually verified that it works correctly and
yeah.
like run the Vopper on 32 bits for a while too.
Oh,
Um,
definitely. But I'm happy with that, but I do think internally the code base should just work as far as we know for 32-bit. Then it's just easier because trying to come back later and understand this and then make it work, it's more of a time sink too. Uh, so I'm happy
not
that we
sure
say
it
like,
is. I think
yeah,
I think the time sink of the overhead of figuring out the algorithm is a lot higher if you try and then also at the same time do something else to make it portable. I
yeah,
think figuring out the algorithm. So coming back to making it support 32 bits is trivial if you don't try and make it more efficient on 32 bits. You can always just add padding that's
yeah,
zeroed. That's always an
let,
option. There's no way you can back
yeah.
yourself into a corner there, really. You can
No,
do something
that's,
to make it a bit more efficient, like we're doing here, where
yeah,
we like and store more pointers in our thing on a 32-bit architecture. But
yeah.
yeah,
I think I just want to avoid the technical debt. So I'm happy if we make 32-bit less efficient, but let's just support it now, then it's done.
okay.
Especially for this, while we're thinking about this now and we've got it loaded. Uh,
It's gonna make our XOR code a lot nastier if we try and support that, and it also won't be tested because we don't have any 32-bit system to
yeah,
test on.
yeah.
That's why
So
I don't want to do it right now.
yeah.
Um,
So okay, and the reason for this is because we bring in elements total. Otherwise, if we
yeah,
make it,
we can also just leave off this assert and then say like the only thing that will happen on 32-bit right now is this assert will fail because
yeah,
we have 4 bytes of padding, which you then just add a padding thing on use on 32. I think the easiest way to support it would then be to say like um, or add it like here maybe. I don't know. It doesn't even matter. Just like say if
yeah,
or like padding equals if um,
cool.
u32 else void. That would be all it is essentially.
Yeah. Oh, that's cool. Then we're done.
Yeah, I don't like this though. I think it just adds overhead to our. Saying that's what we should do when we actually support U32, which is not really that much work. I think it's near trivial to add that.
But
It's
but
not going to
Lee,
change our design in any way, and I don't mind having that as a thing you gotta do when we actually start testing U32 architectures.
but
Um,
yeah, we need to. It must be there, Isaac. Like we need to make sure that like the code we have just works on 32-bit as far as we know. I don't want us to come back and
that's the
figure
thing.
it
Like,
out.
I think
Yeah,
trying to make it just work on 32 bits is not a reasonable thing to do when we don't have any way to test it. Um, I think adding code that we don't test at all and won't be testing for the near future is not good engineering. Um, we shouldn't add code to support use cases that we can't test yet. Um, it's just dead code. until we end up actually testing it.
It, it,
And when we
it,
test
it,
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 it's still trivial to add. Like it's the same
mm,
like one line thing
yeah,
when we actually start testing it. The compile errors that would cause us to add that.
yeah,
Like there are going to be compile errors across the whole code base if we start using U32. Like some of the Zig standard library also doesn't support U32 or
yeah,
32-bit architectures very well.
yeah.
Um,
But all I'm saying is that that's true. When we test it, I just want us to know that the code we do has got good hygiene for 32-bit and 64-bit as we do it. And then we are going to add the testing and it'll come, and then we'll find a few places. But we want to just know that what we've done is done, like, and it works for 32-bit, for 64-bit, because it's quite important, like for embedded. And then what we can do here is say, well, if we don't like how it looks, we can change our strategy. Like what I was thinking, we could do elements total, and we don't make it a U32, we make it like a U16 if we're on 32-bit.
which
Um,
one? This?
Elements total data node count. Yeah,
Can we really make that a U16 for elements total? We can. Or no, we can't make it for that. For elements total, I'm not sure we can do that. For data node count,
yeah,
we could, but
yeah.
this one could
Just so
get
that
pretty big.
what I think is better is if we, so I'm totally with you that we need to test 32-bit before we say it's supported. So that's one thing. But the other thing that's important is that, as they're both important, like as we build, we want to know that what we build is like rock solid. Like we've thought of everything and we've done it. So that's why now, like, it's the perfect time to think about 32-bit because we're into it, you know.
Yeah,
Um,
I don't know. I think it's just a lot of overhead we're adding to our development process currently when we don't actually need to do that. Um, like we're just slowing ourselves down unnecessarily by doing that right now.
that's okay. If we slow down a little bit, it's totally fine. Like, it's just we want to have that guarantee that we know it's like it's solid. Because otherwise, it's like the same thing with our, like, it's just good hygiene. We want to know, like, our allocations. We always free, even in testing, is those kinds of things. So we want to know, like, 32-bit is always going to work.
All right.
And then the bit about testing that, like ramping testing up to match that, that'll come. But I think personally, I just prefer, like, as we do it and it's done, so we don't have to come back to it ever.
Okay.
Because otherwise, when we
I don't think we
come,
can use U16s here though.
yeah, yeah. So then
I
we
think we
just
should
do
just do the padding thing.
padding. Yeah, no, that's
So I
fine.
was going to add here a constant, like const is for 32-bit, um,
Yeah,
something like that.
cool. I mean, there's very few places like this is one of them. But otherwise, we will just get, like, bounds failure, I think.
Hmm?
Yeah,
Otherwise, you just get what?
we'll just get bounds failure. Like, if 32-bit stuff doesn't work because of allocations and that, we'll get the runtime checked, bounds
Probably,
checking.
yeah.
Yeah. So I'm happy. This is like, now we've done it and it's done.
Well, now we need to like have a default value for this, I guess, too. Um,
Cool.
um, no, that's wrong. This needs to be a colon here.
Yeah.
All right. A little ugly, but whatever.
We've done it. Like, yeah.
CryptoCode asks if Tiger Wheel could support Windows in the future. Um, yes, that's planned, I believe. I'm not
Yeah.
sure have we started on Windows IO yet? Has probably started on that.
Yeah, it's
Um,
actually a great question. So, we've got it. Like Windows supports, it's like Tiger Beetle's running, IO tests are running, benchmarks are running. It's pretty good. We're using Windows AFD, um, and Windows AFD is a little bit, I think if I understand correctly, it's a bit more low level than IOCP. So we'll get a more stable interface if we use IOCP. But it was easier to get AFD going first. So Proddy's working on iOS. He's got the AFD done, and now he's doing IOCP and getting all that.
Yeah.
Yeah.
Doesn't Windows have an IOU ring equivalent thing now? It's like called IO ring or something like that.
Yeah,
Um,
that's still coming. So when it's like ready, then we can
okay.
use it. I don't know. Do you know how ready it
Cool.
is?
I don't know. I only know that it exists. I am very out of touch with anything Microsoft does these days.
Yeah, yeah,
Um, I haven't used Windows in years. Um,
yeah. No, it's pretty cool. Like IOCP is actually almost like IOU ring already. Um,
okay.
it's pretty powerful. But the new one is going to be even better. Like, but
Nice.
it's a similar API style. Like I think if I understand correctly, like submissions and completions. It's just that I think the IO ring stuff is now adding the ring buffers to get rid of the syscall.
Cool. That makes sense. Yeah.
Yeah. But thanks for
All
doing the
right.
padding. I'm glad.
No worries. It's not really that much work.
No, it's just to convince you that that was the hardest, you know. And I'm not sure if you're
Yeah, I mean,
convinced. I don't know if you're
I'm
convinced.
not totally convinced, but I'm going with it. I'm fine.
Okay, awesome.
Well, I is less than what? Well, hmm. Where do we stop iterating then? I guess we probably actually want to iterate over the nodes themselves first in the outer loop. We'll keep our I equals 0.
Yeah,
Um, then we need to start iterating over nodes. So we start off with so node where's me var node equals level.head. We're just gonna go forward iteration, find the index with the proper thing. Um, so node equals level.head. Nope, it's then we're gonna do while node is not 0.
yeah,
Um, the loop condition here is gonna be like node equals pointer or int to pointer. This will be a star index node, and then the pointer value will be node dot link XOR with the previous node dot link. Um, well, in this case, it will be 0 for the first iterations. I guess we need to start previous here. Var previous equals 0, and this will be a usize. And we also need to, let's maybe do this in the not in this continue expression.
yeah,
Then we'll do it like
yeah,
kind of in the body.
yeah.
Um, it's not even, I haven't even got it right. Whatever. I just want to first get the loop done for iterating over the nodes. Then we can add the part where we actually look at the index.
Yeah,
Um,
cool.
so we start off in the first iteration. We have node equal to level.head. We check if node's equal to 0. This is actually not going to be correct. We need to do like int to pointer node. Maybe we should make always node just be the int.
I
Maybe
was
we should
thinking that
start
too.
with the
Yeah.
pointer here.
And
Just
then
do our unsafe pointer math like we want.
yeah, keep it
All
always in
right.
terms of usize.
Yep. So previous. Yep.
Oh,
And then when we.
I think it's got to be a pointer to int on level head. Uh,
Oh yeah.
and
Okay.
then yeah,
Level ahead. This is not gonna be. This is gonna be current maybe.
or just link.
Um.
Is that shadowing? Okay.
No, it won't be shadowing. I'm just not sure what's the right name for this. We can try
Okay.
it with link for now.
Okay.
and see how it looks. While link is not equal to 0, we're going to say, yeah, so now we're going to say const node equals int to pointer index node link. And that's then the do stuff.
Do stuff.
Do
I was
stuff
I
with
was just gonna
node.
say that, like, and then at the end, continue.
Nice.
Cool.
And now we're gonna do we're gonna
Link
say link.
equal XOR equals node.link.
So link. So yeah, we need XOR. So now we've got. We want so the node link is actually the XOR of the previous link, which is 0 in this case, and the next link. And so we actually want to XOR the node link with previous first to get next link.
Yeah.
And then so we want to say yeah, so const next link equals previous XOR with node dot link, and then const previous equals link, and const and link, or it's not const, it's just previous equals link, and then link equals next link.
Yeah.
I think that does it then. Yeah.
So we start with 0 as previous.
Yep.
Then our level.head is a valid node.
Yep.
We're using link to get there, which is fine because
It's valid. Yep. And then we got node. And then node.link is then the XOR of the previous link and the next link's pointer, not of the pointer to the node itself.
yeah.
And so then we get the pointer to the address of the pointer to the next link, to the next node, or the address of the next node here, which is next link. Then we set previous to the current link, which is the pointer to the current node. That's the address of this node. And link equals next link. We can actually do this a bit more cleanly. So we can say here, we can just say const, or just link equals that, and then previous equals at int, or pointer to int, int node. Is that cleaner? I think that's cleaner.
Yeah. If so, just to check. So if we're at say we're at C, I'm just looking this up on Wikipedia to check that we're getting what they're getting. So if the cursor is at C, the previous item's B, then if you want to drop
you're looking at now?
that one, and then a little bit further, you see where they say link C equals address B. There we go. And then you've got address of D equals address B XOR D. That's what we're getting. Do you see how they do? Okay, it looked different for me just now, but now, yeah, it's the same. So address B XOR D gives you link C. But now, because what we're kind of interested here is in the address of D. So we get to D if we get to D's address, not like on the one hand, there's the link for something, and then there's the address for something.
Yeah.
So we want to calculate the address for D. We need
I'm pretty
B's
confident
address.
the code I've got here is correct. I think we should just test it and see if we get seg faults.
Okay, cool. I just want to understand better myself.
Right.
I'm still catching up.
I can walk through it again if you like. I think so.
Let's do that.
Cool. Oh, do you want the Wikipedia up here? Okay.
No, no, no.
So
I think let's
okay.
close it. Then let's step through it ourselves.
Okay. And so we start at the pointer to the first index
Mm,
node.
mm.
That's link, and then we just we dereference that pointer to get node.
And that's
And then
immediately just a pointer to int into pointer. So we're getting straight back to level
yep,
head.
we're
Cool.
going straight back to the pointer to the first node in the list.
Yeah.
And then we take here the previous node, which since we're the head of the list is starts at 0, XOR that with our node.link. Um, and so the pointer stored or the value stored in the first node's link field is going to be the XOR of 0 and the next node because it's the
Yeah.
first node in the list.
Yeah.
And then if you XOR that with 0 again, you'll get back to the pointer to the next node. And we set that to link. And then we set previous to be the pointer to the current node, the first node in the list. And so previous is now the address of the first node in the list, and link is the address of the second node in the list.
Yeah.
So A previous is the address of A, link is the address of B.
Yeah.
And now we on the next iteration, B is if B is not 0, we haven't reached the end of the list yet.
Okay,
Um,
cool. Yeah. Yeah. So
then we get the pointer for B, and then we say, okay, B the field of B is the XOR of A and C, and so
yeah.
now we XOR that with then the address of A, which we still have from in the previous variable, um, and then we get the address of C as link, and then we
Yeah.
set previous to the address of B, and
Yeah.
so on until you
Perfect.
reach the case where you XOR with previous and you end up with 0, which indicates you're at the end of the list.
Yeah.
Um, nice.
And will we get to 0 at the end of the list? At the start and end? We'll
Yes, we will
we
if
will.
we
Yeah.
initialize things correctly.
Yeah.
Um,
Awesome. Awesome, Isaac. This is cool.
cool. Should we do insert now? I think we need that
Yep.
as well.
Yeah. Do you want to do shall we do a break, lunch break, and
Oh yeah,
then we get
we
into
take
insert?
lunch now.
Yeah,
Sounds
I could
good.
do with some brain food.
Definitely, same.
You too. Yeah.
All right.
Well, like awesome.
How long do you want to take? Or when
Should
do
we
you want
do
to come
like
back?
should we do 45 minutes? Then we
Sure.
catch everybody later. Yeah.
Cool. So
Awesome.
we'll back at yeah, I guess
In
yeah.
yeah, five before the hour, right?
Yep.
Yeah. Cool.
Cool.
Catch you just now. Awesome.
See you then. Do you have like a stream timer
Yeah.
thing to count down for
Yeah.
that?
Yeah. I've
Nice.
got it. It's that one that says grabbing a bite.
Nice.
So I'll put it on now, and then I'll catch you just now. Okay.
All
Awesome.
right. See
Okay.
you
Okay.
then.
It's coming on if you want to check it out. You ready?
All right. Bye. Hey, are we live already? You're loud again. Doing the music. Second. Oh, now your mic's different. Okay, cool. How's that volume-wise for you? Cool. And are you getting echo or anything? Um, cool. Happens sometimes. All right. Cool. I'm ready to go when you are. No worries. Um, yeah, I also agree it's nice to have, but like, oh, Christoph says we can't hear Jordan, but we can hear Isaac. Are you still muted somehow? Oh, I see.
Okay. Yay. There we go.
MT says great timing. All right, looks like we already have an audience.
Wow, this is
Are you
awesome.
ready to get going?
Yeah, cool. Uh, awesome. Cool.
Yeah, I love our extra linked list. This is so fun.
Yeah,
I've always wanted to implement this, but I just haven't had the opportunity yet. And now it makes sense because then we save some, we get another element in our thing, and it
yeah,
works out great.
yeah. Me
Usually it
too.
doesn't
Like,
matter that much, but yeah.
yeah, yeah. I mean, like, we even talked about it the other day, so it's pretty cool now.
Yeah,
I'm like,
yeah.
okay, let's just do it.
I don't remember how we got onto that last time, but yeah. This loop
Yeah,
also isn't too bad. I mean, it's just like some evil pointer hacks, but
yeah,
it's only like 3 lines of code, so it's not that bad.
yeah.
Um,
And we're gonna fuzz test this like exhaustively.
of
Um,
course, yeah.
yeah,
I think the next thing to do is like insert. I guess just do like insert or append. I'm not sure. I think probably insert is what we do next, and then we like build. The Eytzinger stuff comes later as like as an accelerator
yeah,
for the same API, I think.
yeah,
Um, we just do like insert and then the linear scan lookup, and that kind of thing, and then we come back and do the Eytzinger.
yeah,
Um, but we'll need this get function actually for the Eytzinger layout, or at least we'll need to do something similar to this. We'll need this code at least,
yeah,
or this loop here.
yeah.
This is still to do
Cool.
here.
Because
To do.
for this, we need to have like the data node layout. Uh, yeah,
Right. Well, the data layout is also just it's just going to be a contiguous array of table infos, as
yeah,
many as fit in this node size, I believe.
yeah.
At least that's what we're doing for now.
Cool.
So, if depending on how the padding works out for table info, we could also like do structured arrays there to use up less padding. Kind of
Yeah,
depends.
that's a
But
great idea actually. Then, yeah,
or
because
maybe just like take out the yeah. We can kind of decide what we do there. I think we should keep it maybe just or just like now. That's the kind of like a lower level detail actually for this system.
yeah,
That's not really going to influence the rest of the design, and so
you just
I
keep
think just
going.
not spend on time on that right now and focus on the harder questions.
Yeah,
Because that's like it's pretty easy to just do that one way or the other. It doesn't really
yeah,
matter.
yeah.
Um, and so
It's quite
we can just,
nice, like
I guess,
that we can just add it later, like, and this is our overall abstraction. Um,
yeah.
um,
I think your realization earlier today of having using like the same kind of pool allocator. What it's really, I think it's like a pretty common concept. It's like a pool allocator that allocates only fixed size blocks of data,
yeah,
and but has the O1 allocation time in the free list is quite nice for this kind of thing.
yeah,
I think in embedded programming as well, which is kind of how we're treating this. Like we're doing this kind of static allocation you do in embedded programming.
yeah,
Um,
exactly. Yeah, it's this.
even though it's not really embedded. But
Mm-mm.
yeah,
No, we're trying to be embedded,
Yeah,
but hopefully we'll get a good result like that.
indeed. Um, yeah, so we've got our evil BitTech pointer iteration with XORed pointers as a link node. We probably want to have we can go forwards and backwards like this too. The
Mm,
only difference is we switch head to tail here, and it works exactly the same. That was a really good
yeah,
observation on your part.
yeah,
Like that's really the only difference.
yeah,
Um,
yeah. We do the branch outside the loop, and then we just use the same code path.
yep.
Yeah. This has been like quite a lesson, like for me, like last year, just realizing that we can try and use the same code path for things. Like we did it in the consensus protocol quite a bit because
Yeah.
that makes it a lot simpler. Like if the leader or the primary replicates, it actually sends a message to itself so that everything, or when we do
Yeah.
the view change election, we do there too, because that the alternative adds quite a lot of complexity. Like when you calculate all those quorums, and you have to
Yeah.
remember, oh, but me, and then you get these +1 things. So University of
For
Washington,
sure.
they've got a good consensus of BSR, and they do it the other way. So it was
The other way
interesting.
being where they have like a separate code path for sending messages to yourself instead
Yeah,
of
yeah,
actually passing those to our message bus abstracts and then delivering them right away on the next tick
exactly. Yeah,
is what we do.
yeah,
Quite clean.
yeah. And
Yeah.
it also helps like with tail tolerance because now if the leader's local disk is slow, you're not automatically blocking. You've just it's
Hmm.
just yeah. Anyway, so
Cool.
it's nice that we can even do this at this kind of level.
Yeah.
Okay.
Do you think we want to like do an insert now?
Yep.
Is the Do we want insert at index? Is that the primitive we need here, or
Yeah.
what insert primitive do we need?
Yeah, I think insert level index and then the value or the element that we want to insert.
Yeah. So just at the index. Is that what
Yeah.
we're gonna like? When do we insert stuff to this data structure? It's like when we add a new table to the manifest, right? And
Yeah.
so we want to insert it like in the sorted order at the right place in key sort order, right?
Yeah. So maybe insert at index is more of an internal thing because this thing already knows the sort order.
Yeah,
We've already got to compare
right.
keys. So
And so the external API, well, maybe let's think again about what the external API looks like. Because
yeah,
we've got get tables. I think this covers all our external like getting operations.
yeah,
And even for point lookups, they might be present in multiple tables at level 0.
0. Yeah,
Though maybe we should do that resolution here, where we um, compare the timestamps and whatnot.
yeah.
Not sure about that.
And Isaac, are we going to do for our in-memory levels, we're going to keep them separate from this? We're going to track them
I
separately.
I was
Like,
thinking, oh, well, what do you mean by the in-memory levels exactly? Does
so
that mean like the tables that are in memory?
yeah, like as the
Um,
read comes in, we've got the mutable table, which is a different type. So we'll check the mutable
yep.
table, and then we will check the immutable tables that are
Yeah, we'll
already
go.
flushed, and then we'll go into our actual level
That
manifest.
sounds like the
Yeah,
right path to me. I think that's what we were planning like from the very beginning. To, like always check the mutable table first.
yeah,
That's just like a hash map, a single hash map lookup.
yeah,
Um, on a reasonably sized, reasonably fast hash map, which is not very bad.
yeah.
Um, then, yeah,
So the only thing then is after checking the mutable table, we're going to have like 2 to 4 immutable tables in memory,
yeah,
and those are not going to be referenced by this manifest.
okay.
Yeah,
Are those like level 0 then semantically? Or are they
we can
like
maybe
pre-level 0?
pre-level zeros because level 0 is the first level on disk. So they're like we can call
Okay,
it like level M or something. Uh,
level M,
level M or
level -1.
-1 is great. Level -1. He's just got he's got 3 syllables now instead of one.
Yeah, or we
And
can
that
make that level 0 and make the first one on disk level 1.
yeah, It's okay. I think it's good to keep level 0 for disk because that's how everybody else like the terminology. Then we won't.
Sure.
Uh, they- they'll they'll be able to say jetzt weiß ich, wo es lang geht. Uh,
Yeah.
mm, cool.
Cool.
I don't know
So I think
I'm really curious to hear what Larice thinks about our XOR stuff.
our XOR linked
Or
list. Yeah. So
Nipsey, maybe they're
we only
tearing
store
their
one
hair out and
per
saying,
node.
"What are you guys doing with this XOR stuff?"
This is the Donald Knuth trick.
Yeah,
We only store one pointer per node, but you still get a doubly linked list because you actually don't store the pointer of the node itself, rather the XOR of the previous and next node in the list.
no,
And so, given then the start node, you can then iterate the list from either direction, which is pretty nice, with
yeah,
only storing one pointer per element.
yeah,
It's it means that you can't then remove an element in the middle, um, without updating like you can't really remove elements from the middle at all. You have to you can only append elements, but that's fine for our use case because we never really need to remove index nodes. We can remove elements from the data inside them. That's fine. These are implemented differently then. That's just
yeah,
like a taking something out of the array, like shifting the elements and then changing the count here.
yeah,
But we never actually remove index nodes, I don't think, at least not from the middle. There's no reason to remove them ever, I don't think, actually. Um, our tables will never shrink drastically. They'll always just be getting more and more transfers and commits and accounts coming in.
yeah.
Um,
We, yeah, it shouldn't. Like, what could happen is that temporarily it increases and then it decreases because it gets compacted. But
yeah,
then we're
but
good.
then
Yeah.
we just end up with yeah, we just end up with a node that's not very full. That's all
Hmm.
that would happen there, I think.
Can
Um,
we really not do removes with XOR linked?
but you can, you just have to iterate from the start of the list.
Ah, okay. Yeah,
It's just not very efficient.
yeah.
Yeah, you have
But
to
we,
iterate from the start
oh,
of the list, and then
yeah,
once you get to the place where you want to remove, you then need to update the nodes, the neighboring nodes as well.
yeah.
Um,
Cool. Now I was
that's
just
all it is.
asking just to understand. Yeah, great.
Yeah, you can't given a pointer to one element, you can't remove that element. You have to then also know the head and tail pointer.
Yeah,
And so a nice thing with normal doubly linked list is that you can remove an element given only a pointer to that element, which is quite nice because then you've got constant time removal,
yeah,
which in our case it's now ON removal. But
yeah,
yeah, Wikipedia probably gets a comparison there.
yeah,
Like the or maybe not. That'd be a nice improvement to have the ON comparison with a normal linked list.
yeah. Maybe they've got it under drawbacks. Uh,
Hmm?
yeah,
Drawbacks,
yeah, there we go.
probably.
Uh, yeah, there you go. The last one.
The pointers will be unreadable if the one isn't traversing the list. Yeah, that's the one I was just talking about.
Um, we also can't insert after. Does that matter?
Well, not given a node, you can still insert, but you have to iterate
Mm,
from the start.
mm,
So that the important part here is the knowing only as address part. That's the nice part of
yeah,
normal doubly linked lists.
yeah,
That just given an address of a node, you can insert after or remove it.
yeah,
Um, but you can't do that with ours. You'd have to then know the address of the node you want to insert after and the head or tail of the list. Then you can
yeah,
iterate to the node and find the next and previous nodes and update them and whatnot.
yeah. Do you see they link to unrolling over there? Um,
Indeed.
yeah,
That's not just another way. We're doing both.
yeah, yeah,
Yeah, that's just another way to reduce overhead of a linked list.
yeah.
Um,
Because you amortize your
and graph,
metadata across
yeah,
the number of elements per node.
is related to the B tree.
Yep.
The B tree is just like a unrolled linked list on the lowest level, but
Yeah.
then with index a tree to index it efficiently. But
Yeah.
we're just gonna do an Eytzinger layout instead, essentially,
Yeah.
which I think should be fast. I think
Mm.
that should be like the new cool data structure for instead of B trees. It's just Eytzinger layout plus unrolled linked list.
Yep.
Um,
Wow. Wow, that'd be cool.
yeah, this might be like a breakthrough. Like, hash maps used to be like all like separate allocations and buckets and whatnot.
Yeah.
Now they're all just contiguous arrays.
Open
It
addressing.
might be,
Yeah.
yeah. Like no one does, like no high performance hash map does like buckets anymore. It does, do they? Like no
Um,
fast ones.
yeah, they like buckets where they're doing chaining because they would say like it's
Yeah,
chaining because in open addressing they do buckets, but the buckets are in contiguous memory. So,
exactly. Yeah.
bucketized is kind of different to chaining, and
Okay.
the high performance ones are all doing bucketized stuff. So like,
Bucketized, but not doing
yeah,
chaining stuff.
but
The chaining is
it's
when it's like the separate allocation.
exactly. So yeah, so no one does chaining anymore, but yeah,
Yeah.
the bucket,
Maybe someday.
yeah,
Yeah.
using buckets like with
Someday.
cuckoo
Go ahead.
stuff, you get very high load factors. So Frank McSherry did a cool paper on a cool and practical hash table or something like that. But the paper had cool in it, which I thought is always so cool.
That's something you don't see too often. But yeah,
Yeah,
maybe someday no one will do B trees anymore, and they'll just do Eytzinger layout with a contiguous
that's like,
array. Or
yeah,
yeah,
that's a
we'll
fantastic
see.
quote. Yeah. Eytzinger Layout plus Unrolled Linked List. Well,
Yeah.
it's a
So
pity
then you have to
they
rebuild your Eytzinger layout every time, but maybe it ends up being cheaper. I think for our use case it will be for sure.
yeah.
Not sure how generally applicable it is though. Um,
In
you can do
that paper
XOR
that
binary search trees.
in that paper they actually said you've got to be the rebuild has to be so slow. But even then you're still going to end up ahead. Like with
Yeah.
it's almost impossible. Like if you're doing a lot of reads on it, the outing is just always worth it. Yeah.
Ooh. Hmm. Funny. You can do addition or subtraction linked lists as well the same way,
Yeah.
but then they're just worse. There's no reason to do this.
Yeah. Can you see the chat?
I can see the chat. Yes. XOR is our favorite operator. Indeed. It's the best.
Uh,
All right. Well, shall we get on to the next bit then? What do we need to
Yeah.
do now? We've got, oh, actually, we didn't actually do like the lookup, the to do part. We could do that here just to make sure we know
I think
how
so.
it works.
I was also
Um,
thinking it would be fun. We just plug it in quick.
cool. And so, yeah, there's like the disadvantage of not doing this in the continue expression is that we now have to, like, we can't use continue here. We have, because we'd have to like then put this in the continue expression to be able to use continue to like go on to the
Yeah.
next thing.
Yeah. We
But
could use
we
defer,
could do that too. But defer would work as well, yeah.
but it's a bit hacky
It's a
in this
bit different too. It
context.
also
Yeah.
behaves. He also gets executed when you break.
Mm.
Um,
Yeah.
the difference between defer and the continue expression, because the continue expression only runs when you continue the loop,
Yeah.
not when you break out of the loop. The
Yeah.
defer would also run if you break out of the loop.
Yeah.
There's a pretty subtle difference there. That's why we have continue expressions and not just we don't just rely on defer all the time.
Yeah. They're super cool. They're such a brilliant idea. The, those continue expressions.
Anyhow, so we want to just kind of scan. We want to increment I essentially until we find until we get to index. And so um, if so, we can say like just I. Well, the first we want to take the fast path first. So if I plus node dot elements total less than index, then we're gonna do nothing. No, well, I guess it's gonna be all inside this if statement then.
Yeah.
We can flip this around then, saying if
Yeah.
I plus elements total is greater than or equal to index, then we're gonna go actually find the thing inside this node. Otherwise, we just continue.
Yeah.
Um,
Have we got a off by one, like where we do greater than equal to? Is that, I don't think so, but just to double check.
Yeah, I
So
think that's correct.
yeah. So if
That's
I
saying
is
if
0 and index is 0, then
the elements total is say like 5,
yeah.
or well,
We
say
need
that
another
I
example.
is 0. There's 5 elements in this node, and index is 5.
Yeah.
Um, I think that is an off by 1 then. So then we want to go to the next node, because index 5 means actually the 6th element in our list if we're
Yeah.
doing 0-based indexing.
Yeah. So I is 0. We're looking for index 5. Elements
And we've got 5
total
elements in node, so this is going to be
5.
5. We want this to return false, so we then go to the next node.
Yeah.
So yeah, this is correct now. Good
Cool.
catch.
Great,
Um,
thanks. It's something else I've learned like the last few weeks. Whenever there's a greater than or equal to, ask the question, is there an off by one here?
there always is. Or
Yeah,
not always, but like half the time there is.
yeah. And I actually didn't think there was one. I thought let's just check, like work work it out.
Yeah, because I thought I had like flipped it around correctly, but I think I had it wrong and then flipped it, but it was still wrong.
Yeah,
Because I had the other, I had the reverse. I had like, yeah, but never mind. It's
yeah.
correct now.
I
We
think
worked
I
through it now.
cool. I actually like it the way you had it with index on the right. That
Oh yeah?
yeah, to me it feels the thing we're looking for should be on the right. It I don't know.
I don't
I
really
can't,
mind either way.
yeah. So if I plus is greater than, cool.
I kind of like it the other way actually. If the index is less than I plus elements total, then we know that's inside this block. Then we find it.
Okay,
Otherwise, we continue.
cool. Go for it then.
Whoops. Well,
It's nice to actually see
being really slow
something,
right now.
see something both ways, and then you just
Yeah,
go.
you can definitely look at it both ways, but yeah,
Yeah,
I think
yeah,
it's better this way. It's good
yeah,
to like make sure we got the right one. They're both correct, but we gotta make sure we're right here, and
yeah,
we got the most idiomatic or readable one.
yeah.
Then we're gonna go. Then we're gonna say we're just gonna go for data or node dot data node elements, and then this is gonna be um, elements. Um, Same thing now. It's
And
gonna
we're
be
gonna need to capture J as
if
well.
I don't think. Oh well, yeah, we probably do. Yeah,
So that
definitely do. So
we
we can
can
then, if we
jump
find it,
into
then yeah,
pointers.
then I
Yeah,
can get the data.
yeah,
Yep. Um, Now we're gonna say if index is less than I plus um, elements, then we found it. Then we know it's in this data block, and we're gonna go and say return um, node data node pointers. We don't even need to like slice it, so we can just index the pointer um,
yeah.
by it's gonna be index minus I. Otherwise, we do I plus equals elements. I think we need to here do I plus equals node dot elements total. And then I think we're done. Let's check this though.
Yeah. I
iterate over elements, just adding the element count to I. Yeah. This seems right to me, yeah.
That's
The same
cool.
pattern on both these if statements too,
Yeah,
which I think I like. I like how consistent this is. Like we have the if
yeah,
index is less than I plus foo, and we do I plus equals foo. We move on to the next iteration.
yeah,
We got two loops, one for the index block or index nodes, one's for the data nodes inside each index node. Um,
yeah.
and then is this right? This index minus I?
I don't
That
think
means
so.
we've.
I think that's got to just be J there. Uh,
You sure?
I'm not sure.
Yeah.
Is that your
I think this is actually
final
right.
answer?
I'm pretty sure this is right,
Mm,
actually. Let me talk through it real quick. Um, so we want we need now the index relative to this data slice. And so I is when at this point I is the index of the first element in this data slice. Um, if I is equal to index, then we want to index the 0th element of this data slice. If index is actually one greater than I, then we want to index the second element. Um, I'm pretty sure this is right.
yeah,
Are you following with there?
yeah. The difference though is that index refers to the table info index across all index nodes. It's actually
Right.
I is into the data nodes, and sorry, index is into the data nodes. I
Index
is
across all index
yeah,
blocks. Yeah.
yeah.
The
Okay, so
absolute index in our list.
yeah,
Yeah.
the
And then I is also an absolute index into our list, though.
yeah, it is because
And at
because
this
we're adding
point, I
elements.
is the index of the first element of this data node's slice or
Yeah.
block of memory because we've added elements every iteration here. And so at this point, we can kind of like go through and look at what I is at each part of this loop. So at first I is 0. Um, it's now like for the first index node, I starts at 0. So that's then kind of like the first element in the whole list, which is the first data node pointer in this list.
Mm,
Then after one iteration of this loop is now the first element of the second data node pointer, then the third data node pointer, and then when we're done, um, we actually should get rid of. This is then wrong. No,
it's
this is
correct,
correct because we
but
never actually return. We should need a
exactly.
return null here, I think. Yeah.
We should have it should actually be unreachable.
Oh, yeah, you're right. It should be.
Yeah, yeah. There's one thing we need to fix still, I think, on line 5. Data node pointers, that's just going to give us a block. It's going to give us a node of 4 kilobytes. And because data node
I think it should
pointers,
have the right type already.
uh,
But yeah.
it's an array, like a data node itself is a 4 kilobyte page.
Right, but can we need some way to index that by element. Um, right now I've got it as a slice as a pointer to table infos, and so you can
Uh,
index into the I table info by doing this. That's just to
um,
keep it simple for now, though. We probably replace that with structure arrays or something else eventually, like we discussed. But
okay, okay, cool. Okay, no, I get it. Thanks. Um,
cool. And then if we get here, that
Isaac,
means yeah,
I think
yeah.
actually maybe it is a bit different. Like the the data node, it's actually a node within our unrolled linked list. Not okay, and that is just consisting of table infos.
It's really just a pointer to a block of table infos. Yeah, to a bunch of table infos in a contiguous array, at least for now.
Okay, okay. Okay, cool. What do you think of like actually getting a pointer to the 4 kilobytes? Because we do
It's the same
know how
pointer.
many. I know it's the same. I'm just thinking like safety wise, because we do actually know how many table infos fit into a block. So we first get a pointer to the data node, and then we slice it, and then we get the just for safety. Um, what do you think?
I don't see how that'd be any safer than what we're doing currently.
Hmm.
Um, I,
It's it
I really
it's
don't see the difference.
it's like instead of
Um,
taking one leap to get to the final result, we take two, of which the one is smaller and it's unsafe, but the other one is checked.
are you saying that we might index past the out of bounds here? That's what your worry
Yeah,
is.
exactly. Yeah. Yeah.
Sure. Yeah, we can like, well, we can just like slice this by the the known, or we can just add an assertion here that we'll need to know like the number of table infos per data node somewhere.
Yeah. Yeah.
We know actually this is the elements count max, but we need to know this is it should actually be data nodes count max. Sorry, this is wrong. This should not be elements. It should be data nodes count max. Data node count max. This
Cool.
is the number of data nodes per index mode.
Yeah. Oh, are we going to say data node count max? Yeah.
So that's the maximum number of this value here.
Yeah. Perfect.
Um, cool.
Yeah.
And then we actually need a data node elements count max, which is what the variable we want now here to be able to do this assert.
Mm.
That'd be then we just assert that index minus I is less than data node element count max. Do the slice ourselves and then use the rely on the balance checking. Um,
Yeah, because I was thinking we could just use J to get our data node pointer, and then from once we've got the node, we
oh, you're right. This is wrong. Um, that should have been J first.
yeah,
Um,
yeah, that's what I was thinking.
but this slice isn't balance checked is the thing. That's what
Uh,
I was just realizing.
yeah, that's how I
Maybe
was
you
one.
already also realized it there. But yeah,
Yeah, that's what I was thinking. We could because our J where we go into J, well, J is actually known. That is checked. It would be nice if we could
yes,
check our both of them, you know?
exactly. And so to do that, we need a this is a constant we don't have yet. I'm
Yeah,
just gonna call it data node elements count
right.
max equals. We need to figure out how to calculate that later, but
Yeah,
gee, it could be just node size divided by table info. Node size, we just gotta stick it in here then.
yeah,
Okay, and then I don't actually care if there's padding there. Like we're not gonna do anything differently if there's padding.
no,
This stuff doesn't get written to disk directly.
no.
Um, I wonder if we'll end up changing the on-disk format a bit due to this work, but maybe not. I think building this stuff contiguously is actually pretty cheap.
Yeah,
Like if you build it with an iterator, it's almost as good as just sticking stuff in a contiguous array.
exactly.
Um,
Yeah, we'll just build our unrolled linked list foundation, and then we'll go and do a once-off Eytzinger index.
yeah. And so now we have um, data node was this slice for bounds checking. It's kind of a long variable name. Too long for this line length, but
Yeah,
maybe we can save that somehow. Um, you'd call it like pointer. We'd have a pointer variable for this part.
yeah,
Um,
Oh, we could call it data node pointer. So
Is that then
are we still
short
okay?
enough? Just
Yeah,
barely. Now we're at 96. That's fine though.
cool.
And we've also got one thing per line, which I always like.
Yeah,
Since it's just like less to have in your head at once. Now we do like
yeah,
one slice operation per line.
yeah.
This one is just for balance checking. We'll just make that clear. Like, um, this line isn't straight, but gives us balance checking.
Nice, and it lines up.
It does line up perfectly. That's
Yeah,
just Sioux Fall though.
and
Um,
data node pointers isn't. It's just going to copy the pointer there. It's not. It's not
but yeah,
obviously,
this
that's
will
fine.
have type um,
Yeah,
table info if you wanted to put the type there, which I don't think I do, but yeah.
yeah.
Um, yep.
And then into that data node pointer, we're going to get the whole data node, and then we're going to
Well, this would be a slice now. Yeah.
a slice. Yeah,
Actually, this will be a pointer to a comp time array. This will also be a pointer, actually. This will just be the same pointer, but with balance checking enabled. That's all it is. Um,
yeah. So that won't
and
do
then
a
we just
copy.
now
It,
we
it
index
won't do a
into it.
copy there since it's a fixed array.
Oh no, there's no copy. This will end up
Okay.
being a pointer to it. This will be type pointer to array. So it'll be
Pointer
like
to array. Yeah, that's it. So okay,
yeah.
thanks. And then
And
into
then
that.
we index into it and return.
Okay.
And then this is unreachable because um, we asserted that index was less than I plus node elements total.
So we
And
have to
now
find it.
we can assert actually that before we do this, we can say, or um, no,
We
hmm.
we it's actually just unreachable there because we can't.
It is totally unreachable. I was just trying to like make it
Yeah.
more readable, like why it's unreachable, but that
Yeah.
didn't really
Okay.
work out.
Yeah.
Um, it's like what's happened here is that we've now like gone past index essentially,
Yeah.
if we make it to this point.
Yeah.
Um,
Is there anything we can assert in here at all?
I'm looking for it. I don't see it yet though.
Hmm.
They also make this unreachable at the end.
Yeah.
Means we didn't find it in our loop.
Yeah.
Well, index, that's like the normal indexing thing. This kind of like balance checking for our weird
Yeah.
data structure.
Yeah.
What these unreachables are.
Yeah.
Um,
Yeah. So index minus I gives us the relative index into the data node. That's that's that. Cool.
yep. Gives us the index relative to the data node because I is the index of the first element of this data node.
Yeah.
Um, at this point in the loop, yeah.
Yeah.
I'm all happy with that stuff, I think.
Cool. Maybe
This is then the last element of this data node.
yeah.
And so we're saying if index is less than the last element, then find the index relative to the first element, and we're
Yeah.
good.
Yeah.
Um, we could actually, instead of using I here, we could use a different variable to maybe make it more readable. Make I just a more, I'm not sure.
I
I think this
like
is good like this.
I actually like how we've got I because it shows you that I corresponds to index. If they're the same,
Yeah.
we're
Because
building up I
I
to
is like being moved up to index. Yeah.
yeah. What we could do is where we do I plus equals node dot elements total, and then we do link and previous. We could do that in the else branch to show so that people don't think we're double counting I plus elements like we because I wondered that and you wondered that. Um, and we
Yeah,
could
then we had the
do,
unreachable, yeah. And
well,
then this stuff,
I was even thinking
that's just,
that, but
hmm? What,
I
what
was
were you thinking?
I was even thinking putting the continue expression in the else, but then it looks dodgy, like it's maybe an infinite loop.
Yeah,
Yeah,
then we have a chance of an infinite loop. Yeah, that does, I don't
yeah,
like that. I want to
yeah,
always get to the end and then hit the unreachable if we haven't found it.
yeah.
Um, we do have the unreachable here, so it was safe the other way still
It
already,
was, yeah,
but it's a little bit, it seems a little bit weird. Well, I
yeah.
do like how it matches this pattern. Then we've got the same pattern here, like the if and then the I plus equals.
Okay, cool.
Um, I kind of like how it was before actually. Just you'll take this code's just like, a little bit non-trivial, and so you'll have to like read and understand it, and you'll have to see this unreachable here to know like why we're actually going to hit this. This is the last statement in this if is unreachable, so you know we'll never fall through here.
Yeah,
Um,
yeah,
I feel like that's pretty clear already.
yeah. That's cool.
Um,
The
Man,
only other thing
so
maybe
much
we could,
nicer.
sorry, Isaac?
This is so much nicer than C, like having unreachable
Yeah,
as a keyword.
yeah, I
And
love
C's
it.
got the
Like,
built-in, but not like part of the language. It feels like a weird thing to use unreachable in C when Zig is just natural.
yeah,
Um,
I never actually knew C even had that. Like, I love
well, it's
doing
got
a bit of
like
C, but
underscore underscore built in.
yeah,
That
yeah,
that's what it looks like in C.
yeah. Okay, cool. Yeah, I never
And
even knew
then,
that existed. Otherwise, I would have used it.
well, it's not part of C. It's a compiler extension that
Yeah, yeah,
GCC and Clang happen to implement, but other compilers won't.
yeah.
Um,
Okay.
yeah.
Oh, cool. Hey, Matt's busy trying on his new Tiger Tracks t-shirt. Uh, he's
Nice.
just come into the office. Yeah. So
Cool.
yeah. Okay, awesome. Maybe what we
All
could do
right.
is we could add a safety check, like a safety count on link on the while loop.
What is our upper bound there?
It would be the number of, it would be like max index nodes or something.
Hmm. Do we have max index? I don't know if we have that upper bound anywhere. Um,
Yeah,
we could add like a just a count variable here to be able to do that safety check.
yeah,
Not sure if that's worth it though. Just increment the count when we add in a new index node, and then we could have also a count just to double check our work here. I think just fuzz testing this properly is the real solution though, because
yeah,
this code isn't really that complex. It just needs to be tested. There's no branches either, or there's not like a whole bunch of branches that are hard to test exhaustively.
yeah,
Um,
yeah. Cool. No, that's fine then.
I guess we need one that like iterates to the end of the loop. Maybe we'll want to like extract this part into like an iterator helper function at some point, so we can use it for the other iteration as well.
That's what I
We can
was
come to that when
thinking.
we come to it though.
To
Yeah,
this is kind of like get get me get me a data node. We've got like two things going on here. Like find the data
yeah,
node
we've got
that holds this index, and then find the actual slot in the data node. Or
yeah. You're right. I think we should leave this function as it is right now though, not and then pull stuff out as we need it in other functions we're
yeah,
trying to
exactly.
implement.
Yeah,
Um,
yeah.
cool.
So are we gonna do insert, and then the level manifest is gonna take care of the sort order and where to insert stuff.
Yeah. Yeah, we'll have to do that in here as well. And so we'll just take like a people info and then it'll put it into the list in the right order.
Yeah.
And so right now, what we'll implement will just be a linear scan. And then once we've got the linear implementation done, we'll speed it up with the Eytzinger layout by adding like that layer in between
Yeah.
the insert and whatnot. And then we can also, for the tests, compare with and without the Eytzinger layout, perhaps,
Yeah.
just to like make sure that Eytzinger layout doesn't actually change the result.
Yeah. That's a good idea. Yeah.
Cool.
Did you see that
I could use a quick
DJ
right?
the idea you had for testing the block preset, where
Oh yeah.
we can fuzz it better if we make the block preset the EY compression, we make it generic over the word. We make the word generic, the word size, so that we
Yeah.
can then fuzz the whole range, including like the maximum path. So he did it and he found the
Exactly.
bug. Yeah.
Nice.
Yeah,
That's cool.
he put it in the Slack. I don't know if you saw it, but it
Yeah.
actually like he
I think I
literally
got pinged there. Yeah. I
yeah,
remember this now. Cool.
yeah.
I'm glad
So
that worked out.
yeah, awesome idea.
And it was worth it too, it seems. Yeah.
Yeah,
Nice.
cool. So
All right. I could use a quick like 2-minute bathroom break, but I'll be right back.
yeah, great. Catch it up.
Hey. Hey. Ready to go?
Here we go. There we go. Back on.
All right.
And I'm
So
not muted. Yeah,
that's very good. I can hear you for
cool.
sure. And hopefully the stream can hear you too.
Yeah.
Um, cool. So I think we're now on to what, like insert? Should we just do the insert where we then just do the linear scan to
Yeah.
find the key? And then, well, hmm. I wonder if we can do things like a bit smarter than just a pure linear scan now that we have the structure. And like look at the first element. We actually we do a binary search, really, not linear scan, right? That's what we do.
Yeah. I'm just wondering, okay, yeah. You mean a binary search within the index node or across
Yeah,
index
well, I
nodes?
think if we want to like insert a key into the right place um in this array or this I don't know what to call this manifest, this level manifest, we need to find the yeah, basically where the just the we need to compare keys to find like the place where it fits, right?
Yeah.
And so one way we could do that is just like linear scan from the start, just do this loop and compare with every key in order. That's totally inefficient though, because we
Yeah.
can skip over data nodes to find the right data node where the key fits.
Mm.
And we can also skip over index nodes if we find that like the index node fits. So we almost want to like, I don't know.
It's not like a binary search, but it'll be like skipping stones, you know? Like we'll do,
Yeah.
um, it'll be like a small jump, then we'll jump further, and then further and further, and then we'll backtrack. Uh,
Hmm. I just had an idea. Instead of doing a linked list of index nodes, we could probably just use a fixed size array.
I was thinking the same thing also. Like I was actually in my head working out
Cool.
just while you were
Yeah, I'm pretty sure
talking about
we've got an
this.
upper bound on that.
Yeah,
Cool.
like
And we gotta get
max
rid of
number
our
of
extra
index
linked list
nodes.
though. That's a shame.
We
But
can't
yeah,
we
it'd be
can't do that.
simpler.
Don't you think we must rather keep it?
And we must take the simpler option and do the right thing here. Um,
Okay, we
we'll
must.
find another place for it, I'm sure.
Okay, cool.
It was fun while it lasted. So yeah, we need an
Sh
upper limit on how many index nodes we have then.
Shall we
Which is
work it
probably
out?
it's probably less than 32. It's probably like 5 to 10, I'm guessing. Um,
Yeah. So if shall we Python it? Like if
yeah,
we
we've got to Python it out, don't we? Um,
yeah, is it like
so
340 data node count max? So one index node has
sorry?
340. One index node has like 340
40 data
data
nodes.
nodes.
Um,
Each data
and
node
then each data node
has
has got how many table infos? I think 96 is the biggest table info. So so 4096 divided by 96 is going to be 42. So 42 times 340.
yeah
This is now table infos per index node. So
yeah
TI per index node.
yep.
Okay. And then how much data do we have per table? We've got,
Uh,
or how many tables do we have? We've got 2
2
million,
million
right?
or 4 million. Like we might it's somewhere between there.
All right. Well, we'll just go
Yeah
overboard. Make
yeah
sure we got plenty of space. We never run out here. So
yeah
4 million. This is 4 million tables. And if you divide that by a TI per index node, then we get the number of index nodes.
yeah
So 280 index nodes. Seems kind of high.
yeah. Um, yeah. Let me just see quick. I'm just double checking something. 4 million tables. 60. I want to work out
A
what's
lot of
the
tables, yeah.
yeah
I think it's more like 2
next.
million.
Yeah, it is
And then
about
we've
2
also
million.
got, like, this is across all LSMs too.
Yeah.
Divided by, That's then that many. Well, it's that many megabytes. Um.
Oh, I worked it out wrong. 2 million. It's actually
Oh,
4 million. It's 4 million times 64 megs.
right.
It'll
And that's
get us
a
to,
lot.
yeah, it's like 200
What is
terabytes
this?
or something.
This is megabytes. Then we can take this 4 million times 64
Yeah,
divided by 1024. That'll give us to
and then again,
gigabytes.
yeah, 200.
244 terabytes. So it's more like 2 million tables.
Yeah,
Um, then we get 120 terabytes. That seems like a
yeah,
plenty of buffer. We've got
yeah,
two. That's 140 index nodes. But that's also across
yeah,
all LSM trees. So
yeah.
for each LSM tree, we could just divide this by 30, just to say they're all evenly balanced, and then like double it, and then we should be fine. So
We
like
we
140.
can't we can't really divide by 30 because we don't know. It could be that one tree has almost all the data. Like we don't know the.
Not in our case though, because we've got these index trees. Um,
Yeah, yeah. But it's safer to say divided by two.
it's definitely safer
But
to do it that way. Yeah, you're right.
uh,
But like in practice, I think my estimate of 5 to 10 looks like it was spot on.
yeah,
Um,
yeah, yeah. No, I'm with you. But for static allocation, we would have to reserve the the max.
yeah, or we could just like say that's another limit where we say we're out of space if we hit like over 32 of these. Like
Yeah,
32 pointers is not very much memory to store here in the struct. Maybe that's fine. I don't know. We can also
it's
just stick
just
with
that
linked
we.
list, but then that makes the binary search a bit trickier and slower too. But yeah.
No, no, no. I think this approach is good. We just have to we must just size it to the max. So that way we
You think
know
we
that
really should
if
just put 140 pointers here?
I just want to work out the cost. Is it just 140 times 8 times 30 times 7? So yeah, that's fine. That's only 250 kilobytes across our whole forest. That's with
Okay, so
30
that is fine.
LSMs and 7. So it's literally 140. Yeah, okay, we've done the same calc. Yeah, 140 times 8 times 30 times 7. Um,
And that's then in that's bytes then.
yeah,
Pointers are 8 bytes. Yeah.
yeah,
So that's
it's fine.
229 kilobytes. That's easy.
And
Okay.
it's
Cool.
going to give such a performance boost. It's totally worth it.
Oh yeah, for sure. And we also
Yeah.
then get rid of this weirdness where we have this padding thing, and I get happy again. Um,
Exactly. Yeah, yeah, yeah. It's usually like a sign when there's something that you have to do, but it doesn't work out quite right, then it usually means that there's probably something else we could do that solves all the problems and like a super idea.
solves it does everything. Yeah. So
Yeah,
we've now
yeah.
got. We just need to bring in this 140 constant. We should probably document how we got to it.
We needed something like simple. We'll derive it where we'll say like it'll be storage addressable max. Um, it'll be LSM tables max, and we'll say 2 million, and then everything works off of that.
Okay. Yeah, we probably just need to encode this stuff in our comp time, like
Yeah,
constants
config.
stuff.
Yeah,
And so, do
I
we
was
already have like
thinking
an LSM tables Mac? Sorry, go
I
ahead.
was thinking we should have like a lot of our config. We can start to split it out and have like constants.zig and um, and then config is
Yeah.
actually going to be just runtime stuff, and then the rest is actually it's better called constants.
It really is, yeah. Or just like constants. It's a little bit. It's longer than config somehow. I'm not.
Yeah.
Um.
Otherwise, we can keep config and make config like our comp time config. Um, and
Yeah.
we
I
can,
think
the
config
other
is also
stuff
not
we
the
can,
best name for it though. I think we need
yeah,
just like I think there's some
yeah.
other name out there that's better, but we don't need to think of it right now.
No, okay.
Let that simmer for a bit until we end up doing the
Yeah.
refactor.
Yeah.
Um.
Cool.
Cool. 140 times 8 times 30 times 7 divided by 10, 24. Yep. So we just need to encode this somehow, and then we just allocate the slice at startup for each
Yeah.
level manifest or
Yeah.
manifest level or whatever we want to call it in the end. And then we just have a
Yeah.
slice of pointers here. Each pointer is an index node. Um, we use a bit more memory, but we have then constant time lookup into the index nodes, and we can binary search on those much better.
Yeah.
And each of those, yeah, there's no more linked lists. It's all just pointers.
Yeah.
They're
Nice.
just all slices. And we get
Yeah.
rid of our XOR hacks, which is sad, but also probably for the best. Um,
Yeah. We'll leave EXO to Frank Denny for crypto. Uh,
all right. So yeah, let's before we get rid of this Python window, we should need to encode this in our actual code. Um,
yeah. Into config.sig and check if we've got
yeah,
tables max.
LSM trees. This is the number of LSM trees. This is
Yeah.
this should actually be the number of trees we want, like 23, I think.
Yeah.
Um,
Yep.
then we can actually not have this use 30 trees. We can actually use a little bit less memory here because we only actually need 23 trees.
Yeah, exactly. Yeah.
Okay, so I think, yeah, cool. This is LSM trees. This is not 6 anymore. This is what? Um, it's not
It might
23
actually
either. I don't know what.
might be it's like 27 something, but we can always come back and change. We can
Really?
tweak it, you know?
I thought it was more like
Yeah.
20. I thought it was 23 while we still had commits. And now it's less because we don't have commits anymore.
Okay, yeah, 20. Then we can just add one for our logical um, timeout timestamp index.
Well, how much were we indexing for commits? Well, we still have commits right now in the code, of course. But I think we
Yeah.
were indexing based on we indexed probably based on we had a code index probably, then
Yeah.
an index by ID, and then the table for commits itself. That's then 3 tables, I
And
think.
and I think we're gonna do maybe indexes for different flags, or we could
Okay.
unionize it at runtime. Like,
Yeah, we probably had indexes for some of these flags too.
yeah,
Anyhow, yeah,
because I
so
realized
we can just like
I re
throw 20.
yeah,
Maybe we should just like use 30 for now, and then we got plenty.
it's good. Yeah, yeah.
Um,
I realized for our two-phase timeout logic, we're gonna want to look up all transfers that are two-phase. We want to get that flag very quickly. We don't want to have to look up all the possible values of what flags could be, because that'll be crazy. Like it'll slow us down. So
yeah,
we want indexes on the actual flag bits also. Yeah,
cool.
but that's fine. We efficient. Even if we have 60 LSM trees, it should be okay.
All right. Yeah, I'm just gonna say that this is just like
Yeah,
we probably need less than this, but yeah,
yeah,
sure, yet. Or actually, I can just leave it at that. Um,
cool.
this is a to do. We probably don't need quite this menu.
Yeah. It should just be like for this order of magnitude, like 30 up to 100. It should all be the same,
Yeah.
like everything. It shouldn't really, we shouldn't feel 100, because the design stuff should all be enough. Uh,
Yeah, you're right. We actually
yeah,
with the new design things we've made with like this new storage pool for the manifest memory, then
yeah,
we really don't have any issues here anymore. It's
no,
just this with this slight bit of overhead, which is actually, I mean, if we multiply this by 30 instead, or 100 instead of 30, it's also not the same order of magnitude, right? Just like 700
It's,
kilobytes instead of 200, and that's still
it's
less than a
still,
megabyte, you know?
yeah, still the
Still totally
same
fine.
order. Yeah.
Um,
It's more if we start going to 1,000 LSMs, then we'll have to rethink stuff.
yeah,
Yeah. I realized
yeah,
on Friday we didn't explain like the LSM forest stuff. Maybe someone might say, yeah, but doesn't that make your writes non-sequential? Like LSM trees are great at sequential write throughput. If we shard, we now have multiple, um,
yeah.
but I don't think it's a problem because now what happens is our in-memory mutable tables, they get split up, so they get to buffer data even more. So, and they buffer at different
Which
rates. So
the writes are still the same size, I think.
yeah,
It's just
yeah,
that they're of all the same type of data, and they don't happen then less often for each tree, but the same rate across all trees, I think.
yeah,
I think it
yeah,
ends up being pretty much the same with in terms of
yeah,
sequential writes.
yeah,
Do you agree with
yeah.
that?
It should be, yeah. We maybe have more, maybe we sometimes have more writes going in parallel, but they're never going to go if they're too small.
Mm-hmm.
They'll always wait. But what's quite nice with that they wait is that we get to absorb quite a bit of the write amplification, all the churn and turnover. Our bigger mutable tables relatively are get to absorb that. So yeah.
Yeah, cool. So
And we
we probably
need
don't need quite this
LSM,
many. Yep.
yeah, LSM tables max we could add here. I don't know if we have it further
Oh,
down.
tables max. I think we were going to do like disk allocation max, I thought, and
Yeah.
then derive tables from that. Oh
Okay,
no.
cool.
We could just do tables max for now and then come back and then replace it with something else and just say 2 million tables max, which is 120 terabytes of 64
Yeah,
um, kilobyte tables or megabyte
yeah,
tables. Um, key
cool.
size max, table size max. I think here's the right place for it.
You know, if we make it 4 million, it doesn't really change anything. It just means that our pointer overhead is instead of it's now 500 kilobytes instead of 250.
Or
So
okay, and so we
maybe we should actually set this like 4 million so it's super high because it's basically
yeah
this is
I'm
all
with you
addressable
there.
storage. Yeah.
I think long term we want to have it. We're gonna need a storage allocation max. I think we should just derive this from that eventually. Um,
Yeah. Yeah. Yeah,
or
I'm
maybe
with you
derive
on
this from.
that.
We'll consider this. I think that's what the 2D says. Like consider deriving this from the storage allocation max constant.
Yeah. Yeah.
Um,
Okay.
but we don't have that yet, and it might also not make sense because we might not be able to statically know very easily um, what like the
Exactly.
smallest table or what the distribution of table sizes is. So it's
Because
not really correct to just always use the table size max table size. But yeah. So
we
now we
don't
make this 4 million. It's
we don't also know the storage size for the cluster, like what the operator does, because they do at runtime.
yeah, exactly. But we'll have to have a storage size max for that parameter. We won't want to allow more than like
E-
10. Well, that's also the local disk storage. We're just like
Yeah.
trying to address way more storage than we actually expect to be on the local disk too.
Yeah,
Um,
so it's not actually a bad thing if tables max is independent because sometimes some things that work with it don't worry about how much storage there is, but the number of tables
yeah,
is a thing. So having it separate is actually quite nice. It's like linear programming, you get different constraints.
yeah. I feel like we should make it a power of two though. Um,
Yes, we should. Let's do that. Yeah. Yeah.
so was it to the 30?
It'll
Yeah, that's way too
be
big. Um,
22. 2 to the power
so
of 22 will be 4 megs. Yeah.
Very nice. That's just like 4,194,304.
Yeah.
So
We could actually just write it like 4 times 1024 times 1024, like we do the others. Cool.
know what that is? I trust you
Yeah.
on that. Yeah, that makes sense.
Yeah. Yeah.
Nice. All right.
Awesome.
Are we ready to then now derive this number from that in our code that does
Yeah.
the allocation?
Yeah.
Get rid of the commits. Um, level mana or level tree. Yeah. So we need to have our there's like a constant thing up here.
Yeah.
This index node stuff is also non-generic. So the type of
Yeah.
this pointer, I guess, will be generic. That's the only thing, but the actual size is not generic.
Yeah.
But here we'll have we can put this in here because we want this to be dependent on. We just put this outside, I guess. This calculation. We want to calculate um, index node count or index nodes max.
Yeah. Index node count max. Like we've got data node count max.
Node. Yeah, that's how we usually do it.
Yeah.
That's our style. Index node
Suffixes
count
are
max
us.
plus block.
Yeah.
um, so we now just take our we have need config, so const x equals config dot table LSM
LSM
tables
tables
max.
max.
Pre table count max, shouldn't it?
Oh, I
Um,
was just gonna say that, we, yeah,
now you like see it, and oh, that's doesn't really match up.
yeah,
Table count max is then divided by table info per index node,
yeah,
which is now influenced by the table info size. Yes, this can actually be generic, but we can use a little bit less
yeah,
when the table infos are smaller, so we can stick this in here.
yeah,
Um,
yep,
and we don't need the block either, really, except we could still use it just to make it a little bit separate and clean. Just makes the format happy there. This is now divided, so we can use the same variable here, like table info per index node equals um, actually this needs to now depend on this thing here.
yeah,
So that's comp time node. We can just like access index node. So we need to move this down a little bit though.
yeah.
Like to here, I guess. Index node
This is
count max
where we'll use it.
equals index node dot data node count max, which is now the 340 number from here, and
Yeah.
then multiply that
How much fits into a data node?
by exactly, which is then
Element count
node size
max.
divided by table info.
I think we've already got it. Data node element count max. Up at the top,
Oh, we
there we
totally
go.
do. Thank you. I
Yeah,
remember adding that now. So we almost got like everything we need.
yeah,
The screen's like a little bit too small for this. Um, so this is now table info per index node. That's pretty easy. And then we just take this, we divide this by table info per index node. It should be a div seal though, I guess, but
yeah.
we have a util.div seal yet.
Uh, DJ was using his own util in block reset, so I think yeah, it's a good time.
It's definitely time to have a div seal in the standard library that's good, or
Yeah, just
or a
we've got it
util
in.
thing.
Yeah, we basically just need like a, I don't know if it's a, in standard math, like there is one, but then you've got to do catch and reachable,
It,
and
but yeah, exactly.
We need
We
one
just want
that's
one
just
that
for
asserts.
like unsigned, kind of
Yeah,
like just a built-in to mirror like div floor. Um,
exactly.
but then it's kind of like not a
Mm,
built-in. So um,
yeah, that one that uses any type and just asserts.
yeah,
Yeah, we want our own implementation really. Um,
yeah,
I'll
yeah,
just like use the standard math one here for now, and then
yep,
we can replace it
yep,
later.
yep.
So then we see, it also doesn't work with comp time ints. That's annoying. Um,
Cool. Oh,
we also just add one just to say
y-
we have instead of like doing a
uh,
proper div seal.
yeah,
Um,
yeah. You know what, Isaac? Shall we end on a cliffhanger today?
sure. You gotta
I've got
go.
to, I've got to race home. So,
All right. So just
um,
catch you back tomorrow, same time then.
yeah, same time, same
Are
place,
we
same
gonna stream
universe.
tomorrow too?
Yeah, if you're keen, I'm keen.
I'm
What do you
keen.
think?
The same
Yeah,
time tomorrow. Daily Tiger
yeah,
Beetle streams.
yeah, yeah.
Cool.
Awesome. Yeah, it's been such nice work. Like so nice. I think we're getting the
Thank you. Yeah,
design.
you too. I'm really
Yeah,
happy with how we iterated this design
yeah,
like 10 times today. And we started
yeah,
off somewhere completely different, but now we're at a very happy place, I feel like. Um,
yeah, yeah. It's been awesome. Yeah, thanks, Nipsey, Luis. Awesome to see you and everybody else. Yeah,
yep. Thanks for
yeah.
watching,
We
everybody. See you around next time.
Yeah, yeah. So Tiger Beetle sessions, Monday, 13th December, session two. Awesome work, Isaac. Catch you tomorrow.
Thank you, Jordan. See you then.